Hello there, and welcome to the Cosmographer. The emptiest region ever found in the universe contains roughly 4 quadrillion solar masses of matter, which is 2 to 3,000 Milky Ways worth, and not 1 gram of it has ever produced light. That is only number 8 on this list. Further down is the ordinary matter, the kind people are made of, sitting at 1 atom per 20 cubic meters at a temperature near 1,000,000 degrees, invisible because it is too hot rather than too cold. There is a magnetic field out there, older than the first atoms, preserved only because nothing has happened in that region since the beginning to overwrite it. And the entry at the top of this list is not a thing the void contains, but the one thing that fills every cubic centimeter of it at full strength, outweighing everything else in it by more than 10 to 1. 10 candidates for what is really inside the Boötes Void, counted down from 10 to 1, each ranked by how much of that emptiness it actually fills. Get comfortable and settle in. If a long, slow walk through the emptiest place in the universe sounds like a good night to you, a quiet like and subscribe helps this channel reach more curious minds like you. Because by the end of this list, the Boötes Void will not look like a hole in the universe. It will look like a preview of it. Let's begin at number 10. Number 10, the 60 galaxies already on the map. There is a region of space, about 700 million light-years from here, that has spent 45 years being described with the wrong word. The word is empty. It is a useful word, and it is the reason anyone has heard of this place at all, and it is almost entirely wrong. What sits out there in the direction of the constellation Boötes is not an absence. It is a volume 330 million light-years across, in which the ordinary furniture of the universe has been thinned out by a factor of 5, and then filled back in by several things that are present at full strength everywhere and simply do not shine. So this list has a rule, and the rule is worth stating clearly before we begin, because everything that follows depends on it. We are going to work through 10 candidates for what actually occupies the Boötes Void. And we are going to rank them by a single, honest measure, how much of that volume each candidate actually fills. Number 10 fills almost none of it. Each entry after that fills more. And the entry at the top of this list fills every cubic centimeter of it, at exactly the same density it has everywhere else in the universe, which is the reason it wins a countdown about emptiness. We will begin with the part of the answer that has been on the map since the beginning. 60 galaxies. That is the current count of galaxies known to sit inside the Boötes Void, and it is the number that made this region famous, because a volume that size ought to contain about 2,000 of them. 60 where 2,000 were expected is a shortfall of 97%. That shortfall is the entire reason this video exists, and by the time we reach number 1, it will mean something completely different than it means right now. The discovery came on the 30th of September, 1981, in a paper published in the Astrophysical Journal Letters. Its title was plain to the point of bluntness: 1,000,000 cubic megaparsec void in Boötes. The authors were Robert Kirshner, then at the University of Michigan, Augustus Oemler Jr. at Yale, Paul Schechter at Kitt Peak National Observatory, and Stephen Schechtman at the Mount Wilson and Las Campanas observatories. The volume named in the title was The Finding. They had located a region of space roughly 100 megaparsecs across that appeared, to their instruments, to contain nothing at all. The method matters here because it explains why nobody had noticed something so large. This was not a photograph of a dark patch of sky. If you point a telescope toward Boötes tonight, you will not see a hole. The direction is crowded with foreground stars belonging to our own galaxy and with background galaxies lying far beyond the void, and none of them look unusual. What Kirshner and his colleagues did instead was a redshift survey, and specifically a pencil beam survey. They chose 3 small, widely separated fields in the direction of Boötes, and for the galaxies in those fields, they measured recession velocity, which converts directly into distance. What came out of that work was not an image at all. It was a histogram, a simple plot of how many galaxies sat at each distance along the line of sight. And running through that histogram was a gap. Between roughly 12,000 and 18,000 kilometers per second of recession velocity, the counts collapsed to almost nothing. Crucially, they collapsed in all 3 fields at once, which is what ruled out the ordinary explanations. A patch of obscuring dust would have affected one direction. An error in one night's calibration would have affected one field. 3 separate lines of sight, hundreds of millions of light-years apart at that distance, all showing the same gap at the same distance, meant something real was there. Or rather, that something real was not. The numbers as they stand today have been refined but not overturned. The center of the void sits roughly 700 million light-years from Earth, at a redshift of about 0.046, which corresponds to a recession velocity near 13,800 kilometers per second. Its diameter is usually quoted at around 330 million light-years, although that figure carries a caveat worth keeping in mind. The void does not have a surface. It is not an object with a boundary, it is a deficit, and its edges are irregular and fuzzy in the way that a thin patch in fog is irregular. Its total volume is on the order of 1 million cubic megaparsecs, which is where the paper's title came from, and which amounts to something like 0.25% of the entire volume of the observable universe, contained in a single underdense region. 330 million light-years is a difficult number to hold, so here is one way to hold it. It is roughly 1,650 Milky Way galaxies, laid end to end in a single line. Or, if you prefer time to distance, light leaving one wall of the void arrives at the opposite wall 330 million years later. Light that is completing that crossing right now set out when Earth was in the Carboniferous period, when the continents had not yet assembled into Pangaea and the largest thing walking on land was an amphibian. Now to the correction that begins to undo the word empty. Astronomers describe underdensity using a quantity called delta, in which 0 represents the average density of the universe and -1 would represent a perfect vacuum, a region containing literally nothing. The Boötes Void has been measured at roughly -0.8. That is not close to -1. It means the void sits at about 20% of the cosmic average density. 1/5 is a serious deficit, and it demands an explanation. It is also, precisely, not nothing, and the gap between 1/5 and 0 turns out to be large enough to hold everything else on this list. The 60 galaxies that are in there have a second surprise attached to them, which is where they sit. They are not scattered evenly through the volume the way you might sketch it. They lie along a rough tube, a loose filamentary chain that threads approximately through the middle of the region. The standard explanation for that arrangement is elegant. The Boötes Void is probably not one void at all. It is most likely the merged remnant of several smaller voids that grew outward until they ran into each other. When 2 voids merge, the wall of matter that used to separate them does not vanish. It is left stranded in the interior of the combined structure, a filament of galaxies now surrounded on all sides by emptiness that used to be on only one side. That detail is satisfying because of what it implies. The galaxies inside the Boötes Void are not evidence that the region is populated. They are evidence that the region has a history, and that the history involved several separate emptinesses becoming one. The galaxies themselves are worth a moment, because void galaxies are a recognizable population with recognizable habits. The Void Galaxy Survey, led by Rien van der Weijgaert and collaborators, studied around 60 of them using the Westerbork Synthesis Radio Telescope alongside optical imaging, and the profile that emerged is consistent. Galaxies in voids are bluer than galaxies of the same mass in the walls and filaments. They are lower in mass overall. They are richer in neutral hydrogen. They are later in morphological type, meaning more spiral and less elliptical. And they are forming stars faster relative to the stars they already have. Their hydrogen disks are typically smooth, symmetric, and undisturbed, which follows directly from their address because there is nothing anywhere near them to disturb anything. In galaxy clusters, the members are constantly stripped, harassed and starved by their neighbors and by the hot gas they move through. None of that happens in a void. The standard phrase for void galaxies is late bloomers. They are galaxies whose assembly is running slow, not because anything went wrong, but because nothing has ever come along to speed it up. It is worth saying plainly that the Boötes Void is not a defect in the universe, and not a hole punched into anything. It is the expected outcome of gravity operating for 13.5 billion years on the tiny density variations imprinted in the cosmic microwave background. Regions that started very slightly overdense pulled matter inward and became the filaments, walls, and clusters we call the cosmic web. Regions that started very slightly underdense gave matter up to their surroundings and became voids. Matter drained out of the Boötes Void because that is what matter does when it is in a place with slightly less gravity than the places next to it. Voids in general occupy roughly 80% of the volume of the universe, while holding a small fraction of its mass. They are not the exception in the cosmic web. By volume, they are most of it. One small clarification is worth making, because the name causes confusion. The constellation Boötes is the herdsman, and its brightest star is Arcturus, which sits 37 light-years away and is one of the closest bright stars to Earth. The void has nothing whatsoever to do with those stars. It lies in the same direction and roughly 20 million times farther out. The constellation is only an address, the way a street name is an address, and the stars that make the shape are practically in our lap by comparison. There is also a puzzle attached to the void galaxy population that has never been fully resolved. In 2001, the cosmologist James Peebles named it the void phenomenon. Voids appear to be emptier of small dwarf galaxies than the simplest predictions of cold, dark matter cosmology allow. The simulations produce plenty of low-mass structures in void interiors. The surveys do not find them. Either the physics suppresses those galaxies more thoroughly than the models assume, or they are there and we cannot see them. Hold that fork in mind, because both branches of it turn up later on this list, and both of them add to the inventory rather than subtracting from it. Nor is Boötes the largest such region we know about anymore. The Eridanus supervoid, identified in 2007 by Lawrence Rudnick, Shay Brown and Lilia Williams, may be around 1.8 billion light-years across. The local underdensity described by Ryan Keenan, Amy Barger and Lennox Cowie in 2013, sometimes called the local hole, may be roughly 2 billion light-years across, and if it is real, we are inside it. But Boötes was first. It is the cleanest example, and it remains the one everybody names. Which brings us to the sentence that has followed this region around for decades, and which we will return to at the very end of this list, because by then it will mean something else entirely. The astronomer Greg Aldering, considering what it would be like to live inside this place, observed that if the Milky Way had happened to sit at the center of the Boötes Void, we would not have known there were other galaxies until the 1960s. Sit with that for a moment, because it is not rhetoric. From the center of the void, the nearest galaxy beyond the wall would be more than 160 million light-years away. That is not merely faint. It is categorically out of reach of the instruments that actually built extragalactic astronomy. Edwin Hubble established that Andromeda was a separate galaxy in 1924 using the 100-inch telescope at Mount Wilson, and he could only do it because Andromeda is 2.5 million light-years away, and he could resolve individual variable stars inside it. Move that same galaxy 65 times farther out, and the individual stars are gone, and the whole object is a smudge below the detection threshold of every plate he ever took. An astronomer on a world at the center of the Boötes Void would build a perfectly correct astronomy. They would map their own galaxy accurately. They would work out stellar evolution and nuclear fusion and the distances to their own neighboring stars. And they would conclude, entirely reasonably, on the basis of excellent observations, that their galaxy was the universe. Picture that sky for a moment, because it is stranger than a black sky. Standing on a world near the center of the void, looking up, the first impression is that nothing is wrong at all. The home galaxy is overhead, a band of light across the sky, its stars in their usual crowds and its dust lanes cutting through in the usual way. It looks the way our sky looks. The difference only appears when you try to look past it. There is no Andromeda smudge low in the north. There are no Magellanic clouds hanging off to one side. There are no faint elliptical companions, no satellite galaxies, no dim patches that resolve into something else when you point a telescope at them. The dark between the stars simply goes on being dark, all the way out, at every magnitude any eye or early telescope could reach. It is not an ominous sky. It is a complete sky that happens to be missing a universe, and there is no way to tell the difference from the inside. Which is worth remembering when we consider the 4 astronomers who found this thing in 1981 and what they must have done first. There is a gap in your data. It is a gap where 2,000 galaxies should be. And the first thing any careful person does with a result like that is assume they have made a mistake. Check the calibration. Check the second field. Check the third. Somewhere in that process, the third field agreed with the first 2, and the explanations that involved human error ran out one by one, and 4 people became the first human beings to know that the universe contains regions like this. And then they had to decide whether to publish it. They published it, and the number they published, 60 galaxies where 2,000 were expected, has been treated ever since as a measurement of how much is out there. It is not. 60 is a count of the galaxies in the Boötes Void that our surveys were built to see, which is a different quantity entirely. And the gap between those 2 numbers is where the next entry on this list lives. Number 9. The galaxies too faint to count. The reason a galaxy is hard to see is not the reason most people assume. It is easy to imagine that detection is about total brightness, and that a survey finds the bright galaxies and misses the dim ones. That is not how it works. The quantity that actually decides whether a galaxy makes it into a catalogue is surface brightness, which is the amount of light arriving per unit area of sky, measured in magnitudes per square arcsecond. And surface brightness behaves in a way that is genuinely counterintuitive, because it means that spreading a galaxy out makes it harder to find, even if not one photon has been lost. Here is the number that governs everything. The night sky, at a good dark observing site, with no moon and no city, has a surface brightness of roughly 22 magnitudes per square arcsecond in visible light. The sky itself glows. airglow in the upper atmosphere, faint scattered starlight, zodiacal light from dust in the solar system. All of it adds up to a background that is never black. A galaxy whose light per patch of sky falls below that value is competing against the sky's own glow, and no straightforward amount of exposure time solves the problem, because the longer you expose, the more sky you collect too. So take a galaxy with a perfectly respectable number of stars and spread those stars over 10 times the area. The total light is unchanged. The surface brightness has dropped by 2.5 magnitudes, and the galaxy may have crossed from easily detected to effectively invisible. Bigger is not easier to see. Bigger at fixed total light is harder. The case that proved this to astronomy was found in 1986 by David Malin, working at the Anglo-Australian Observatory on photographic plates from the UK Schmidt telescope. Malin had developed his own techniques for photographic amplification, chemistry rather than electronics, involving stacking plates and unsharp masking to pull out contrast that was there but unreadable. Using those techniques, he found an object now called Malin 1. Malin 1 is a spiral galaxy, roughly 650,000 light-years across. You could lay 6 Milky Ways side by side across its disk. It sits about 1.19 billion light-years away, and the surface brightness of that enormous disk is around 26 magnitudes per square arcsecond, which is roughly 100 times fainter than the night sky it is seen against. At its center, it has a perfectly ordinary bar and a perfectly ordinary bulge, the sort of thing any survey would catalogue without comment. What it also has is an enormous, nearly transparent skirt of stars extending far beyond that, and that skirt is what makes it one of the largest spiral galaxies known. The important part is not that Malin 1 is large. It is that Malin 1 had been sitting inside the field of view of every photographic survey that covered that patch of sky for decades, and nobody had seen it. It was not hiding behind anything. It was not obscured by dust. It was simply below the threshold, in plain view, for as long as photography had been pointed in that direction. The class of object that Malin 1 turned out to belong to has expanded considerably since then. In 2015, Peter van Dokkum and Roberto Abraham reported 47 new objects in the Coma cluster using an instrument called the Dragonfly Telephoto Array. Dragonfly is an unusual telescope, and its design is directly relevant to this entry. Instead of a mirror, it is built from an array of commercial Canon telephoto camera lenses operating together as one instrument. The current configuration uses 48 of them. The reason for that choice is that the nano-fabricated coatings on those lenses suppress scattered light far better than any conventional mirror, and scattered light is exactly what drowns a low-surface brightness object. What Dragonfly found were galaxies as large across as the Milky Way, carrying something like 1,000th of the Milky Way's stellar content. The class was named ultra-diffuse galaxies, and the discovery quietly reset the assumption that the galaxy population had been more or less fully mapped in nearby clusters. It had not. A whole category had been below threshold. The extreme member of that class was reported in 2016. Dragonfly 44, in the Coma cluster, had a measured internal velocity dispersion that implied a total mass in the region of 1 trillion solar masses, which is comparable to the Milky Way, while carrying roughly 1% of the stars a galaxy that massive should have. The headline that followed was a galaxy that is 99.99% dark matter. That claim has since been revised downward as better measurements came in, and the object remains contested, and it is worth saying so plainly because the credibility of everything speculative later on this list depends on the established material being handled honestly. Dragonfly 44 is extreme. it is probably not as extreme as the first announcement suggested. The Coma cluster, where all of this was found, is worth anchoring for scale, because it sits about 320 million light-years away. That is a distance almost exactly equal to the width of the Boötes Void itself. So when we say that a whole category of galaxy was hiding at Coma's distance until 2015, we are saying that it was hiding at a distance smaller than the diameter of the region this video is about. The Boötes Void is more than twice as far away as Coma. Whatever dragonfly found at Coma would be 4 times fainter again at the Void, and it was already at the edge of what a purpose-built instrument could reach. How an ultra-diffuse galaxy comes to exist is still argued over, and the competing explanations are worth naming because each one implies a different population in a void. One idea is that they are failed galaxies, objects that assembled a large halo, began forming stars, and then lost their gas early to some catastrophe, leaving a wide, thin, permanently underlit disk. Another is that they formed in halos with unusually high spin, which spreads the gas over a much larger radius before it can collapse, and so produces a galaxy that is diffuse from birth. A third is that they are ordinary dwarf galaxies that have been tidally puffed up by repeated passes through a cluster. A fourth is that they inflated themselves, with early supernovae driving gas outward, dragging the dark matter's gravitational potential outward with it, and leaving everything more spread out than it started. Those explanations matter for a void because they do not all survive the environment. Tidal puffing requires a cluster, and there is no cluster in the Boötes Void. Early gas loss to a hostile environment requires a hostile environment. But the high spin route and the self-inflation route work perfectly well in isolation, which means that void interiors should contain ultra-diffuse galaxies formed by mechanisms that need no neighbors at all. Nobody has ever looked for them there with an instrument capable of finding them. The opposite anomaly also exists, which is the strangest part of the whole story. NGC 1052 DF2 and its neighbor DF4, reported in 2018 and 2019, are ultra-diffuse galaxies that appear to contain almost no dark matter at all. Their globular clusters move too slowly for there to be an invisible halo around them. So the class includes objects that are almost entirely dark matter and objects that are almost entirely not, which suggests that whatever makes an ultra-diffuse galaxy has more than one recipe. Now let us apply all of that to the Boötes Void, because the arithmetic is the point of this entry. The current interior galaxy count for the Void comes largely from the Sloan Digital Sky Survey, which reaches roughly 22.2 magnitudes in the red band for reliable detection of an extended object. At the Void's distance of 700 million light-years, that threshold corresponds to detecting galaxies brighter than an absolute magnitude of about -16. There is a further small penalty from redshift, since surface brightness dims as 1 plus the redshift raised to the 4th power, which at the Void's redshift costs about 20%. Small, but working in the same direction. So what does a threshold of -16 absolute magnitude actually catch? Apply it to our own neighborhood, and the answer is immediate and uncomfortable. It catches the Milky Way. It catches Andromeda. It catches Triangulum. It catches the large and small Magellanic Clouds. And that is essentially the whole list. The local group has well over 100 known member galaxies. Take that entire assembly of 100+ galaxies, place it at the distance of the Boötes Void, observe it with the instrument that produced the Void's galaxy count, and it registers as 4 or 5 objects. 60 is not a count of the galaxies in the Boötes Void. 60 is a count of the galaxies in the Boötes Void that are bright enough and compact enough to have made it into a catalogue. The true number could be several times higher without contradicting a single measurement anyone has taken. And this is not a hypothetical shortfall, because we know exactly what the missed population looks like. The local group's ultra-faint dwarf galaxies contain only hundreds to a few thousand stars each. Several of them were found only because the Sloan survey could resolve their individual stars against the sky, one point of light at a time, and then notice that those points clustered in a way that random field stars do not. That technique works at 200,000 light-years. At 700 million light-years, it is not merely difficult, it is impossible in principle with any telescope now operating, because you cannot resolve individual stars in a galaxy that far away. There is a naming coincidence here worth clearing up before it causes confusion. There is a galaxy called Boötes Void, a dwarf spheroidal found in Sloan data in 2006 at a distance of about 197,000 light-years. It is in the constellation. It has nothing to do with the void, and it is roughly 3,500 times closer. It is, however, a good illustration of exactly the kind of object the void's census would miss entirely, since a galaxy with a few thousand stars is not detectable at extragalactic distances by any means we currently possess. It is worth pausing on how strange the selection effect is when you state it directly. Low-surface brightness galaxies may make up a substantial fraction of the galaxy population by number, while contributing only a very small fraction of the total light in the universe. That means two different censuses of the same volume can disagree by a large factor, and both be correct, because one is counting objects and the other is counting photons. Almost every statement in popular astronomy about how many galaxies exist is derived from the photon census, because that is the one our instruments perform automatically. The object census has barely been attempted outside our own immediate neighborhood, and the bias runs in a consistent direction. Every selection effect in this entry removes the same kind of galaxy, the wide, thin, gas-rich, slowly assembling, low-mass kind, which is, from the previous entry, exactly the kind of galaxy that voids preferentially produce. The void galaxy population and the undetectable galaxy population are described by nearly the same adjectives. Our surveys are not randomly blind, so they are blind in precisely the direction that matters most for the region we are examining. There is a way around the problem, and it involves looking at something other than starlight. Neutral hydrogen radiates at a wavelength of 21 centimeters, whether or not it has ever formed a star, which makes radio surveys a completely independent census of the same volume. The Alfalfa survey, the Arecibo Legacy Fast Alpha survey, completed in 2018 after covering roughly 7,000 square degrees, catalogued around 31,500 hydrogen sources. Some of what it found were gas-rich objects with too few stars to have appeared in any optical catalogue. The Void Galaxy survey used the Westerbork array in the same spirit. Radio hydrogen and optical starlight are two different accountings of the same sky, and they do not agree. Hydrogen has one further advantage that matters specifically for voids. Neutral hydrogen is destroyed by ultraviolet radiation, so in crowded regions near hot young stars, it is constantly being ionized away. In a void, there is very little ultraviolet radiation and very little to disturb a gas disk, so hydrogen survives in larger, flatter, more extended configurations than it manages anywhere else. The Void Galaxy survey found exactly that: hydrogen disks that are noticeably wider relative to their stellar disks than in comparable field galaxies. If there is a population of gas-rich, star-poor objects anywhere in the universe, a void is where it should be easiest to detect at 21 centimeters and hardest to detect in visible light. What is coming will settle a good deal of this. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will image the entire southern sky repeatedly for a decade, and the stacked depth it reaches will go several magnitudes below Sloan. That is precisely the regime where low surface brightness objects stop being invisible and start being obvious. The square-kilometer array will do the equivalent for neutral hydrogen. Within the working lifetime of most people listening to this, the galaxy count for the Boötes Void will be measured again by instruments that are not blind in the way the current ones are, and the number 60 will be replaced by something larger. It is a rare and pleasant situation in science, incidentally, a number that is very likely wrong, a clear understanding of why it is wrong, a clear understanding of which direction it is wrong in, and a specific instrument already underway that will correct it. 60 is not a mystery. 60 is a placeholder with a scheduled replacement date, which is the honest way to end this entry. Every statement anyone has ever made about how full or how empty the universe is has been made from inside a well-lit neighborhood, using instruments built to find things that shine, by observers who are themselves made of the kind of matter that shines. The universe we have catalogued is the universe that happened to be bright enough to make it into a catalogue. But a galaxy too faint to see is still a galaxy. It still collapsed, still gathered gas, still lit its first stars. The next entry on this list is the population that did all of that except the last part. Number 8. The halos that never lit up. Before we go any further, we should weigh the thing. Everything so far has been a discussion of what can and cannot be seen, and that is a conversation about instruments. There is a different conversation available, one that does not depend on detection at all, and it is simply arithmetic. We know the average density of matter in the universe to good precision. We know the volume of the Boötes Void. And we know, from the density contrast measurement, that the void sits at roughly 1/5 of that average. Those three numbers multiply together, and the product is not a small one. Here is the calculation, done slowly. The mean matter density of the universe is about 2.7 times 10 to the minus 27 kilograms per cubic meter. That is a genuinely tiny number, a couple of hydrogen atoms in every cubic meter of the universe, averaged over everything. The volume of a sphere 330 million light-years across is about 1.6 times 10 to the 73rd cubic meters. Multiply those and then take 1/5, because that is what the void's measured underdensity requires. The answer is on the order of 4 quadrillion solar masses. Let us put that into a unit a person can actually hold. The Milky Way, including its dark matter halo, weighs something in the region of 1.5 trillion solar masses. 4 quadrillion divided by 1.5 trillion is somewhere between 2 and 3,000. The Boötes Void, the most famous emptiness in astronomy, the region that has been called a hole in the universe for 4.5 decades, contains roughly the mass of 2 to 3,000 Milky Way galaxies. It is not short of matter. It has never been short of matter. What it is short of is places for that matter to be concentrated. That is the single most important sentence in this video, and everything from here to number 1 is an elaboration of it. So it is worth being precise about where those thousands of galaxies worth of mass actually is, because if it were in galaxies, we would see it, and we do not. Roughly 85% of the matter in the universe is dark matter. It has been measured a dozen independent ways, from the rotation curves of individual galaxies to the way clusters bend light to the pattern of acoustic peaks in the cosmic microwave background, and every method returns the same ratio. Dark matter does exactly one thing that we can detect. It gravitates. It emits no light at any wavelength. It absorbs no light at any wavelength. It reflects nothing, scatters nothing, and passes through ordinary matter and through itself, as though neither were there. A region of space can contain thousands of Milky Ways worth of it and present itself to every optical telescope and every radio dish and every X-ray satellite ever built as an empty field. So the honest picture of the Boötes Void's mass budget is this. Something like 3.4 quadrillion solar masses of dark matter and something like 600 trillion solar masses of ordinary matter. The dark component is undetectable by construction. We will come back to the ordinary component later on this list, because its story is stranger. For now, the question is what shape the dark matter takes. It does not take the shape of a smooth fog. That is the picture most people carry, and the simulations disagree with it emphatically. The Millennium Simulation, run by Volker Springel and collaborators in 2005 with 10 billion particles, and its successors Bolshoi and Illustris TNG, all produce the same structural result. Dark matter does not stay smooth. It collapses under its own gravity into bound clumps, called halos, at every mass scale the simulation can resolve, and in cold dark matter models the hierarchy continues, far below what any simulation can resolve, down to masses comparable to the Earth, and in some formulations, well below that. And voids in those simulations are not featureless bubbles. They come out with an internal hierarchy of their own, a faint, scaled-down version of the cosmic web, with tendrils and minor filaments and low-mass halos strung along them, the same architecture as the large-scale structure, but at much lower contrast. Ravi Sheth and Rian van der Weegaert worked out the formal description of how voids evolve, including the two modes that matter most, void in void, where small voids merge inside larger ones, and void in cloud, where a small void forming inside an overdense region is squeezed out of existence. The tube of galaxies threading through the Boötes Void is the observational fossil of the first of those processes. So a void is not the absence of the cosmic web. A void is the cosmic web at low amplitude, running the same structure formation as everywhere else, more slowly and more faintly. Which raises the obvious question. If the void is threaded with dark matter halos, and halos are where galaxies form, why are there only 60 galaxies in it? The answer is one of the more elegant pieces of physics in cosmology, and it is called reionization. For the first few 100,000 years, the universe was an opaque plasma. Then it cooled enough for electrons and protons to combine into neutral hydrogen, and the universe became transparent and dark. It stayed neutral and dark for a few 100 million years. And then the first stars and the first quasars switched on, and their ultraviolet output flooded outward and stripped the electrons back off the intergalactic hydrogen. That process, spread across the period from roughly 400 million to 1 billion years after the beginning, is reionization. And it did something else besides ionizing the gas. It heated it to something like 10 to 20,000 Kelvin. Hot gas moves fast. Gas at 20,000 Kelvin has a characteristic thermal speed of several tens of kilometers per second, and a dark matter halo can only capture gas whose thermal speed is below the halo's own escape velocity. Below a threshold of roughly 30 kilometers per second of circular velocity, corresponding to halos below something like 100 million to 1 billion solar masses, the halo simply cannot hold onto the gas. The gas is moving too quickly for the halo's gravity to matter. It cannot accrete. It has nothing to make stars out of. It never forms a single star, ever, for the entire history of the universe. Now here is the part that applies specifically to voids. In a dense region, a small halo has escape routes from that fate. It might be fed by a cold filament of gas dense enough to resist heating. It might merge into something larger before the ultraviolet background switches on, becoming part of a halo that is above the threshold. There are neighbors, and neighbors provide options. In a void, there are no filaments to feed it, and nothing nearby to merge with. The suppression operates at full strength with nothing to interfere, which produces a prediction that ought to be much more famous than it is. The Boötes Void is the place in the observable universe where the fraction of dark, starless halos should be highest. Cold dark matter cosmology predicts that its interior contains a very large population of gravitationally bound structures that have never contained a single star. How large depends entirely on where you set the mass floor, and the mass floor in cold dark matter models runs absurdly low. If even 1% of the void's 4 quadrillion solar masses sits in halos above 100 million solar masses, that is, tens of millions of individually bound, individually invisible objects inside one region of sky. And we have direct evidence from our own neighborhood that this suppression is real rather than a convenient theoretical assumption. It is called the missing satellites problem, and it was raised independently in 1999 by Anatoly Klypin and collaborators, and by Ben Moore and collaborators. The simulations predicted that a galaxy the mass of the Milky Way should be orbited by hundreds to thousands of bound subhalos. The observed number of satellite galaxies at the time was a few dozen. That is not a small discrepancy. It is a factor of 10 or more, and it was one of the first serious challenges to cold dark matter. The resolution has come from both directions at once. Deep surveys have found many more satellites than were known in 1999, most of them ultra-faint dwarfs with a few thousand stars, and the count keeps rising. And the reionization argument explains why the rest are dark rather than absent. Both halves of the answer say the same thing. The halos are there, and most of them never lit up. There is a related and still open puzzle called Too Big to Fail, raised by Michael Boylan-Colchin and collaborators in 2011, which points out that the most massive predicted subhalos are the ones that most conspicuously fail to have obvious galaxies in them, and those are the halos that should have been too large for reionization to silence. The threshold itself has a name worth knowing. Below a virial temperature of about 10,000 Kelvin, hydrogen cannot cool efficiently by atomic line emission, which is the primary mechanism by which gas sheds energy and falls to the center of a halo to make stars. That is the atomic cooling limit, and it sits very close to the same mass scale that reionization heating picks out. Two independent pieces of physics converge on the same boundary. Below it, a halo is dark. Above it, a halo is a galaxy. The Boötes Void is full of halos, and the question is, what fraction of them cleared that bar? There is one further difference between void halos and halos elsewhere, and it is a subtle one with real consequences. A halo's concentration, meaning how sharply its density rises toward the center, is set largely by how early it assembled, because a halo that formed when the universe was denser inherits that density in its core. Void halos assembled late, gently, and from low-density surroundings, so they are systematically less concentrated than halos of the same mass in the walls and filaments. A less concentrated halo is a shallower gravitational well, which makes it even worse at holding onto hot gas. Everything about the void's structure conspires in the same direction. Now, none of that would be worth much if starless halos were purely theoretical. They are not. They have been detected. Just not there. The cleanest method is strong gravitational lensing. When a distant galaxy sits behind a massive foreground galaxy, its light is bent into multiple images, and the exact positions and relative brightnesses of those images depend on the detailed mass distribution in the lens. Put an invisible clump of mass near one of the images, and the image shifts and dims in a calculable way. Simona Vegetti and Leon Koopmans developed the gravitational imaging technique that turns that effect into a detection, and it has found individual dark subhalos in lensing galaxies down to masses of around 100 million to a billion solar masses. Objects with mass, with gravity, with a measured position, and with no detected starlight whatsoever. The population exists. The technique simply cannot be pointed at an arbitrary patch of empty sky, because it requires a lens and a background source to be lined up. Voids themselves have been weighed the same way. Because a void is underdense relative to the cosmic mean, light passing through it is very slightly demagnified, which is the inverse of ordinary gravitational lensing. The signal from any single void is far too small to measure. But identify thousands of voids in a large survey, such as the Dark Energy Survey or the Kilo Degree Survey, and stack their lensing signals together, and the void weak lensing effect emerges from the noise. It has been detected, and it has been used to measure the average density profile of voids from their centers outward. We have therefore weighed voids gravitationally without ever seeing what is inside them, which is precisely the situation this entry describes. There are also individual candidates for what a dark halo looks like when it holds a little gas. Virgo He 21, reported in 2005 by Robert Minchin and collaborators using Jodrell Bank and Arecibo data, is a cloud of neutral hydrogen in the Virgo cluster, containing around 100 million solar masses of gas, with a rotation signature implying a total mass of order 100 billion solar masses, and no detected starlight at all. It is contested, and it should be stated as contested. A competing reading interprets it as tidal debris torn from the nearby galaxy NGC 4254, rather than a self-contained dark object. High 1225+01, catalogued by Riccardo Giovanelli and Martha Haynes in 1989, is another isolated hydrogen cloud with an apparent dark component. And closer to home there is the Smith cloud, a high-velocity hydrogen structure about 11,000 light-years long, currently falling toward the Milky Way's disk at roughly 73 kilometers per second and due to arrive in about 27 million years. Matthew Nichols and Joss Bland Hawthorne argued in 2009 that the Smith cloud must be held together by a dark matter halo, because a cloud of loose gas would have been shredded during its previous passage through the disk, and it plainly was not. There is even a named prediction for what a starless halo should look like if it manages to retain any gas. Alejandro Benitez Lambe and collaborators, working from the Apostle simulations in 2017, described reionization-limited hydrogen clouds, small, round, pressure-supported pockets of neutral hydrogen sitting inside dark halos, held in equilibrium with the ultraviolet background, with no stars and no optical counterpart of any kind. That is exactly the object a deep enough hydrogen survey of the Boötes Void might find, and exactly the object no optical survey ever will. And there is a reason to care about the count beyond bookkeeping, because the abundance of low-mass halos in voids is one of the sharpest available tests of what dark matter actually is. Cold dark matter predicts structure all the way down to very small scales. Warm dark matter, made of lighter and faster particles, free streams out of small overdensities before they can collapse and erases the bottom of the hierarchy. So counting what is in a void is not an inventory exercise. It is a direct question put to the dark sector about its own nature, and voids ask it more cleanly than anywhere else, because there is nothing else going on to confuse the answer. The nearest thing we have to that measurement comes from inside our own galaxy. Stellar streams are the stretched-out remains of star clusters and dwarf galaxies torn apart by the Milky Way's tides, and they form long, thin, delicate ribbons of stars. Anything massive passing through a ribbon leaves a gap. The stream designated GD1 shows gaps and density perturbations that Anna Bonacca and collaborators reported in 2019 as consistent with an impact by a compact, massive, entirely dark object. Not a star cluster, because there is no cluster there. Something with the mass of a small galaxy and none of the light. Two further methods are being built for exactly this problem, and both are worth knowing about because both will eventually be pointed at voids. The first is astrometry. Space telescopes that measure stellar positions to extraordinary precision, of which Gaia is the current example, can in principle detect the slow gravitational tug of a passing dark mass on the apparent positions of background stars. The second is pulsar timing. Millisecond pulsars are natural clocks of astonishing regularity, and a dark object passing near the line of sight to one changes the light travel time by a measurable amount. Neither technique is sensitive enough yet for a halo 700 million light-years away, but both are sensitive to precisely the kind of object that emits nothing, and both are improving. It is also worth pausing on how thoroughly the alternative has been searched for. If dark matter is a particle, then for 40 years experiments have been trying to catch one. Detectors buried under mountains, cooled to fractions of a degree above absolute zero, shielded from every known source of background, waiting for a single dark matter particle to strike a single atomic nucleus hard enough to register. Xenon, argon, germanium, silicon, sodium iodide. Every generation of experiment has improved sensitivity by orders of magnitude, and every generation has returned the same result, which is nothing. That null result is not a failure, it is a steadily tightening constraint. But it means the substance that makes up 85% of the matter in the Boötes Void has never been observed in a laboratory, only inferred from what it does to things we can see. So the picture at the end of this entry is a strange one, and it should be allowed to settle. The emptiest place we know of contains more mass than every galaxy any human being has ever named, arranged into an unknown number of bound structures, none of which have ever produced a single photon. And the only reason we call the region empty is that none of it caught fire. And notice what has happened to the original number along the way. 60 galaxies where 2,000 were expected sounded like a description of scarcity. What the weighing shows is that the scarcity was in one very specific commodity, the commodity of matter that has been compressed hard enough and cooled fast enough to ignite fusion. Every other commodity is present in quantities that would take a lifetime to write out. The void did not fail to receive its share of the universe. It received its share and then spread it across a volume so large that nothing in it ever reached the density required to become visible. That distinction between not having and not concentrating is going to be the difference between every remaining entry on this list and the ones we have already covered. Everything so far has been bound to something. Every galaxy, every faint disk, every dark halo is a thing held together by its own gravity, sitting where it formed. The next entry on this list is what is loose. Number 7. The Wanderers. Galaxies leak. That is the fact this entry rests on, and it is better established than most people realize because it can be photographed. Point a large telescope at a rich galaxy cluster, expose for long enough, and process the image carefully enough to separate the real sky from the instrument's own scattered light, and something appears between the galaxies. Not stars in the foreground, and not a background object. A faint, smooth, diffuse glow filling the space between the cluster members, extending for millions of light-years, with no obvious source. It is called intra-cluster light, and it is produced by stars. Stars that are gravitationally bound to the cluster as a whole and to no individual galaxy within it. In the Coma and Virgo clusters, intracluster light accounts for something in the range of 10 to 20% of all the starlight the cluster produces, and some measurements run considerably higher. Those stars were once inside galaxies. They were pulled out during close passes and mergers, when two galaxies swung past each other and the tidal forces stripped material from both, and the stripped material did not fall back. It stayed in the cluster, orbiting the cluster's overall gravitational field, no longer belonging to anything smaller. That intracluster light has also become a useful tool in its own right, because it turns out to trace the cluster's total mass distribution more faithfully than the galaxies do. The galaxies are lumpy and few, the stripped stars are smooth and numerous, and they settle into the dark matter's gravitational shape. Astronomers now use the diffuse glow as a visible proxy for the invisible mass, which is a small and satisfying reversal. The part that people find hardest to accept is that individual intergalactic stars have been identified, one at a time, and confirmed. In the Virgo cluster, astronomers including Magda Arnaboldi and John Feldmayer picked out intracluster planetary nebulae. A planetary nebula is the glowing shell of gas a sun-like star throws off as it dies, and it radiates most of its light in a few very narrow emission lines, which makes it stand out against a broad-spectrum background far better than an ordinary star does. That narrowness is what makes the detection possible at 50 million light-years. Each one is a specific star at a specific position, with no galaxy anywhere around it, confirmed to exist and confirmed to be alone. Galaxies do not only lose stars gently, they also fire them out. In 2005, Warren Brown and collaborators, working with Sloan data, found a star receding from the Milky Way at roughly 709 kilometers per second. That is well above the escape velocity of the galaxy at that star's position. It is not on a long orbit. It is leaving permanently, and it is never coming back. The class is now called hypervelocity stars, and several dozen candidates are known. The mechanism was worked out in 1988 by Jack Hills, and it is beautifully economical. Take a pair of stars orbiting each other as a binary and send that binary on a path that brings it very close to the supermassive black hole at the center of the galaxy. The black hole's tidal field pulls harder on the nearer star than on the farther one, and the pair is torn apart. One star is captured into a tight orbit around the black hole. The other departs with the binary's entire orbital energy transferred to it, moving far faster than anything in the galaxy has any business moving. The Hills mechanism therefore predicts that hypervelocity stars should come in pairs with a captured companion left behind near the center, and several candidate captures are known orbiting Sagittarius A star. The current record holder was reported in 2019 by the Southern Stellar Stream Spectroscopic Survey and is catalogued as S5HVS1. It is moving at about 1,755 kilometers per second, and its trajectory traces back cleanly to the galactic center roughly 4.8 million years ago. There is no ambiguity about where it came from or where it is going. Now, honesty requires a constraint here, and it is a significant one, so we will state it plainly rather than let the impression stand uncorrected. At 1,000 kilometers per second, crossing 330 million light-years takes something like 100 billion years. The universe is not yet 14 billion years old. No star ejected from the walls of the Boötes Void has had time to cross it. The picture of a void busy with transiting stars is not correct and should not be implied. What 13 billion years does by at those speeds is a journey of roughly 40 million light-years. That is enough to carry an ejected star far clear of its parent galaxy, well past any halo, and a long way into open space. So the correct picture is not a void crossed by wanderers. It is a void whose every wall galaxy and whose 60 interior galaxies have been quietly surrounded for billions of years by expanding shells of things that left and did not stop. And stars are almost certainly the smaller half of that population. Microlensing surveys have spent 2 decades demonstrating that planets can be unbound too. The optical gravitational lensing experiment, OGLE, monitors many millions of stars toward the galactic bulge, watching for the brief brightening that occurs when an unseen mass passes almost exactly in front of one of them and focuses its light. The duration of the brightening scales with the square root of the lensing object's mass. So a star produces an event lasting weeks, and a planet produces one lasting hours or less. The events that matter here are the very short ones. OGLE 2016 BLG 1928, reported by Premec Mroz and collaborators, lasted 41.5 minutes from start to finish and is consistent with a free-floating object of roughly Earth mass. Statistical analysis of the whole population of ultra-short events has produced an estimate that is startling on first hearing. Free-floating and wide-orbit planets may outnumber the stars in the Milky Way by something like a factor of 2. The mechanism for producing them is the ordinary business of building a planetary system. Simulations of young systems routinely go through a chaotic phase in which forming planets scatter off one another gravitationally, and in a large fraction of those simulations, at least one body is thrown onto a hyperbolic trajectory and leaves for good. Our own solar system is thought to have ejected material during its early rearrangement. If most planetary systems eject at least one world, then every galaxy has been running a slow, continuous export of planets for its entire existence. Some of those departures are not solitary. When a star is ejected gently enough, its planets go with it, still in orbit, still keeping time. So a fraction of the free-floating population is not free-floating at all, but is orbiting a star that is itself unbound, a complete miniature system sailing out of its galaxy intact. There is a line of published work on rogue planets that is worth including here, because it changes the emotional temperature of the whole entry. A planet without a star is not necessarily a frozen corpse. A world with a thick hydrogen atmosphere retains heat extraordinarily well, and a world of Earth's mass generates a steady internal supply of it from the decay of radioactive potassium, uranium, and thorium in its interior, which is the same source that keeps Earth's own core molten. Combine those two, and a rogue planet can in principle hold a liquid water ocean beneath an insulating ice shell for billions of years, with no star involved at any point. The energy budget is small, but it does not run out quickly, and it does not depend on being anywhere in particular. Whether anything could live in such an ocean is not something anyone can answer. What can be said is that Europa and Enceladus, in our own solar system, maintain subsurface liquid water using tidal heating from a giant planet rather than sunlight, and that they are treated as serious targets in the search for life. A rogue planet's ocean would be heated differently, but it would be an ocean, in the dark, stable over geological time. The Boötes Void's population of such worlds is unmeasured and unmeasurable, and it is not zero. The first proper census of free-floating planets is being built now. The Nancy Grace Roman Space Telescope is designed with a microlensing survey as one of its primary missions, staring at the galactic bulge with a wide field and a rapid cadence specifically to catch the short events that OGLE can only sample. It should turn the current statistical estimate into an actual number, and it should extend the sensitivity to considerably lower masses. That census will be of our own galaxy, not of the void, but the ratio it establishes between bound and unbound worlds applies everywhere galaxies exist. Now let us do the arithmetic for the void, because the number that falls out of it is the best way to feel what a void actually is. Take the 60 known interior galaxies. Assume something on the order of 10 billion stars each, which is conservative for a population of small, late-type galaxies. Assume that 10% of their stars have become unbound over cosmic time, which is at the low end of what intra-cluster light measurements imply for cluster environments. That gives roughly 60 billion free-floating stars inside the Boötes Void. 60 billion is a very large number. Now spread it through the volume. The result is approximately one wandering star per cube of space, 68,000 light-years on a side. 68,000 light-years is roughly the width of the Milky Way's stellar disk. So the picture is a cube the size of our entire galaxy, containing one star. Then another cube the size of our galaxy next to it, containing one star. And so on, in every direction, for 330 million light-years. The number 60 billion and the number 1 per galaxy-sized cube are both correct, and holding both of them at the same time is what it means to understand a void. It is a useful corrective to the way emptiness is usually described. The Boötes Void does not fail to contain stars. It contains, on this conservative estimate, roughly as many free-floating stars as there are stars in a small galaxy, and they are simply arranged so thinly that no two of them will ever influence each other in any way. They will never collide. They will never pass close enough to perturb each other's motion. Over the entire remaining lifetime of the universe, essentially none of them will interact with anything at all. That is a different condition from absence, and it does not have a common word attached to it. Detecting any of them is a different matter. There is exactly one way to identify a specific intergalactic star at extragalactic distances, and it is to wait for it to explode. Hostless supernovae have been found in several cluster surveys, supernovae that flare in a cluster field with no detectable host galaxy anywhere at their position, no matter how deeply the position is imaged afterward. Each one is a confirmation that an individual star was sitting alone in intergalactic space at that exact spot. It is an absurdly inefficient detection method, requiring you to be watching the right patch of sky at the right moment, while a star that has waited billions of years finally dies, and it is the only one available. The few that have been studied have compositions consistent with having formed inside a galaxy and been ejected later, which is exactly what the intra-cluster light picture predicts. It is worth noting how the number scales, because the estimate above was deliberately conservative in every direction. If free-floating planets outnumber stars by a factor of 2, as the microlensing statistics suggest, then the void's population of unbound worlds is well over 100 billion. If the interior galaxy count is several times higher than 60, as the previous entry argued it probably is, multiply again. If the unbound fraction is closer to the 30 or 40% that some cluster measurements suggest rather than the 10% used here, multiply once more. None of those adjustments change the qualitative picture because the volume is so enormous that even an order of magnitude more objects only shrinks the typical separation by a factor of about 2. That is the arithmetic of a void in one sentence. You can be wrong by a factor of 10 about how much is in there and barely change how empty it feels. The wandering population is not only stars and planets. Brice Menard and collaborators demonstrated in 2010 that dust extends far beyond the visible edges of galaxies by measuring the very slight reddening of background quasars as a function of their angular distance from foreground galaxies. The signal persists out to megaparsec scales, which means galaxies are surrounded by dust halos vastly larger than themselves. So the void's outer regions contain stray stars, stray planets, stray stellar remnants, and stray dust. It contains, in other words, the raw material of everything, at a concentration far too low to ever assemble into anything again. The remnants deserve a mention of their own. When a massive star dies, the supernova that produces a neutron star is frequently asymmetric, and the resulting kick gives typical neutron stars speeds of around 400 kilometers per second. A substantial fraction of those exceed galactic escape velocity. Every galaxy has therefore been exporting neutron stars for as long as it has been making massive stars, and those are objects that emit almost nothing once their rotation has slowed and their magnetic fields have decayed. Consider what it would be to ride alongside one of those wanderers on the outer margin of the void, 8 billion years into its journey. The surface underfoot is rock, or ice over rock, a few degrees above absolute zero. There is no sun. There has been no sun for longer than the Earth has existed. There is no day, no season, no shadow that moves. And the sky above is not black in the way a night sky is black, because there is no bright thing anywhere in it to define the darkness against. The nearest galaxy is a faint patch that would take a good telescope to distinguish from nothing at all. In the whole visible field, there is no landmark, no reference point, no object close enough to change position over any span of time a mind could hold. The planet has been traveling for 8 billion years and has covered a small fraction of the distance to the far wall, and it will still be traveling when the galaxies it left behind have run out of gas and gone dark. At 68,000 light-years of typical separation, the nearest neighboring object to that world is so far away that no telescope built on its surface, of any size, would resolve it as anything but a point. Stars and planets are not the only things a galaxy can lose. The next entry on this list is what happens when a galaxy loses its center. Number 6. The black holes with nowhere to live. A galaxy can lose a star without much difficulty. Losing the object at its center requires something considerably more violent, and the physics that does it was only worked out properly in the last 20 years. Gravitational waves carry momentum. That is the starting point. When two black holes spiral together and merge, they radiate an enormous quantity of energy as ripples in space-time, and if that radiation is emitted symmetrically, the momentum cancels out and the merged object stays put. But the radiation is not symmetric in general. If the two black holes have different masses, or if their spins are misaligned with each other and with the orbital plane, the gravitational waves are beamed preferentially in one direction. And momentum radiated in one direction must be balanced by the remnant recoiling in the other. This is called gravitational recoil, or more colloquially, a kick, and calculating it required solving Einstein's equations numerically for the full merger, which was not possible until a breakthrough in numerical relativity around 2005. Once it was possible, the results were larger than most people had expected. Work published in 2007 by Manuela Campanelli, Carlos Losto, Josef Zlokauer, and David Merritt, and independently by other groups, showed that certain spin configurations produce recoil velocities in the range of 3,000 to 4,000 kilometers per second, with the most extreme arrangements approaching 5,000. Those configurations acquired a name. They are called superkicks, and they require the two black holes to be of roughly equal mass, to be rapidly spinning, and to have their spins lying in the orbital plane and pointing in opposite directions. That is a specific arrangement rather than a typical one, but with hundreds of millions of galaxy mergers in the history of the universe, specific arrangements happen. Now the comparison that makes the number mean something. The escape velocity from the center of the Milky Way is around 600 kilometers per second. A superkick is several times that. So when two galaxies merge and their central supermassive black holes eventually find each other and coalesce, the result does not necessarily settle quietly into the center of the new galaxy. With the wrong spin alignment, the merged black hole is fired out of the galaxy that made it, carrying millions of solar masses with it, and it does not come back. It is worth taking a moment over what that departure would actually look like from the outside, because the scale of it resists intuition. Two galaxies have merged, which is not a collision in any ordinary sense. The stars are so far apart that essentially none of them strike each other, and the process takes hundreds of millions of years of the two systems passing through one another and settling. Deep inside, the two central black holes sink toward the middle through dynamical friction, dragging on the surrounding stars, gradually losing energy until they are bound to each other. Then they orbit for a long time, tightening, until they are close enough for gravitational waves to take over. The final stage is fast. In the last few orbits, the two objects are moving at a substantial fraction of the speed of light, and the entire merger completes in a fraction of a second. In that fraction of a second, an amount of energy comparable to the rest mass of several suns is converted into gravitational waves, and the newly merged black hole, weighing perhaps 100 million times the mass of the sun, begins moving. There is no explosion visible. There is no flash. There is a bright accreting disk at the center of a galaxy which, over the following millions of years, is simply somewhere else, then somewhere further, and eventually outside the galaxy altogether, dragging the innermost part of its disk along with it, and slowly running out of fuel. The galaxy left behind is now a galaxy without a central black hole, and it will not get another one unless it merges again. The natural question is whether anyone has ever seen this happen, and the honest answer is that there are several candidates and no confirmations. It is worth going through them, and worth being clear about the uncertainty attached to each, because this entry is going to make a claim about what could be sitting in a void, and that claim is only worth anything if the observational record is presented accurately. The oldest candidate is HE0450-2958, reported in 2005 by Pierre Magan and collaborators in Nature, and immediately nicknamed the Naked Quasar. It is a bright quasar, unmistakably powered by an accreting supermassive black hole, and deep Hubble imaging failed to find a host galaxy around it. A quasar with no galaxy is exactly what an ejected black hole should look like, since it would carry its innermost accretion disk with it and keep shining for a while. Later work argued that a host is present but heavily obscured or lost in the quasar's own glare. The case is not settled, and it is generally no longer treated as the strongest example. CID 42, in the Cosmos survey field, shows a compact bright source clearly displaced from the center of its galaxy, with a relative velocity near 1,300 kilometers per second, measured from the offset between its broad and narrow emission lines. 3C186, analyzed by Marco Kierberge and collaborators in 2017, is generally considered the strongest case of the lot. A quasar sitting roughly 11,000 light-years from the center of its host galaxy, moving at about 2,000 kilometers per second relative to it, in a galaxy that shows clear signs of a recent merger. That is the full expected signature, in the right order. B31715 plus 425, reported by James Condon and collaborators in 2017, using very long baseline interferometry, appears to be something even stranger, a supermassive black hole that has been stripped of nearly its entire galaxy, moving at around 2,000 kilometers per second and trailing debris behind it, like a seed pulled out of a fruit. And then there is the most visually extraordinary candidate, which is also the most contested. In April 2023, Peter van Dokkum and collaborators published a Hubble image containing a feature that nobody had a category for, an extraordinarily thin, almost perfectly straight streak of young blue stars and shocked gas, roughly 200,000 light-years long, extending away from a small galaxy. 200,000 light-years is twice the diameter of the Milky Way. The streak was not a jet, because jets do not form stars along their length. It was not a tidal tail, because tidal tails curve. Their interpretation was a wake. A supermassive black hole of around 20 million solar masses ejected from that galaxy, moving through the tenuous gas outside it at close to 1,000 kilometers per second, compressing the gas ahead of it the way a boat's bow compresses water, and leaving behind it a contrail of gas that had been squeezed hard enough to collapse into new stars. If correct, it would be the first direct observational proof that supermassive black holes get ejected from galaxies. The caveat has to be stated, because the story has moved on. Subsequent spectroscopic work, including analysis of infrared spectra, has been argued to be consistent with the feature being an edge-on star-forming galaxy seen in projection rather than a black hole wake. That reading explains the straightness, the blue color, and the star formation without any ejected black hole at all. The question is open. Both readings are live. A video that presented the wake as settled would be misrepresenting the state of the field, and the speculative entries later on this list are only worth listening to if the established ones are handled straight. There is a useful way to think about why these cases are so difficult to confirm, and it comes down to the fact that every one of them is an argument from absence. A quasar with no host galaxy might be an ejected black hole, or it might be a quasar whose host is too faint to see, which brings us straight back to the surface brightness problem from earlier on this list. A displaced bright source might be a recoiling black hole, or it might be two galaxies in the process of merging, seen at an angle that makes one nucleus look offset from the other. A straight streak of stars might be a wake, or it might be an ordinary galaxy that happens to be very thin and viewed exactly edge-on. In each case, the ejection explanation is more interesting, and the mundane explanation is more likely, and the only way to tell them apart is with data that is currently at the edge of what instruments can produce. This is what a genuinely open question looks like from the inside, and it is worth showing rather than smoothing over, because the alternative is a list of confident claims that quietly fall apart when anyone checks. Supermassive black holes are the dramatic case. The numerous case is much smaller and much more common. The Milky Way is estimated to contain on the order of 100 million stellar mass black holes formed from the collapse of massive stars over the galaxy's lifetime. That figure comes from stellar population modeling rather than from a count, since the overwhelming majority of them have never been observed and never will be. And many of them received a kick at birth. When a massive star's core collapses, the supernova that follows is frequently asymmetric, and the newborn compact object recoils. Typical natal kicks run to hundreds of kilometers per second, and a fraction of them exceed the galaxy's escape velocity. So every galaxy that has ever existed has been slowly exporting black holes into whatever surrounds it, for its entire lifetime, at a rate nobody can measure. The walls of the Boötes Void are where this matters. Voids are bounded by sheets and filaments are where galaxies encounter each other and merge. So the boundary of the void is precisely the region where mergers have been happening for billions of years, and precisely the region from which any ejected black hole would be launched. Half of those ejections, on average, would be aimed inward. A black hole leaving a wall galaxy at 2,000 kilometers per second travels roughly 80 million light-years in 13 billion years, which is not enough to cross the void, but is more than enough to put it well inside, far from anything, permanently. Nobody has counted them because nobody can. But the mechanism is established, the geometry is favorable, and the timescales work. If supermassive black holes are ejected from galaxies at any appreciable rate, then the outer regions of every large void in the universe should contain some number of them, sitting in the dark with nothing to fall into them. Now, why a void hides them perfectly? A black hole is detectable in exactly 3 situations, and it is worth going through all 3, because in the Boötes Void, all 3 fail for different reasons. First, it can be accreting. Material falling toward a black hole forms a disk. The disk heats through friction to extraordinary temperatures, and it radiates. This is how nearly every known black hole was found. But accretion requires something to accrete, and the amount of light produced scales sharply with the density of the surrounding gas. In the Boötes Void, the gas density is so low that the resulting luminosity, calculated straightforwardly from the standard accretion formula, falls many orders of magnitude below any detection threshold. It is not dark because of mystery. It is dark because of arithmetic. Second, it can be orbiting something whose motion betrays it. This is how black holes in binary systems are weighed, by watching the companion star swing around an unseen mass. In a void, there is nothing nearby to orbit, and nothing nearby to be orbited by. Third, it can pass precisely in front of a background star and lens it. This requires a dense field of background stars for the alignment to occur with any reasonable frequency, which is why microlensing surveys point at the galactic bulge. In the direction of a void, at that distance, there is essentially nothing to line up with. The difficulty is not theoretical, and there is a single case that demonstrates exactly how hard it is. In 2022, after roughly 6 years of painstaking Hubble astrometry, astronomers announced the first confirmed isolated stellar mass black hole. It was found through a microlensing event, catalogued as OGLE 2011 BLG 0462, and the object turned out to be around 7 solar masses, about 5,000 light-years away, drifting through the galaxy at roughly 45 kilometers per second. One object. 6 years of follow-up. Inside our own galaxy, against one of the densest star fields in the sky, with a lensing event to point the way. That is the state of the art for finding a black hole that is not doing anything, and it explains, without any exaggeration whatsoever, why the black hole population of the Boötes Void is a complete unknown. It is worth adding one detail about what such an object would be doing out there. A black hole in a void still interacts with the cosmic microwave background, and it still emits Hawking radiation. But the Hawking temperature of a stellar mass black hole is around 60 billionths of a Kelvin, which is far colder than the microwave background at 2.7 Kelvin. So it is absorbing more energy than it radiates. Every isolated black hole in the universe is currently, very slowly, growing, and will keep growing until the expansion of the universe cools the background below its own temperature, which will take an extraordinarily long time. There is one further population that deserves mention because it is the least constrained of all. Intermediate mass black holes, in the range of hundreds to many thousands of solar masses, sit awkwardly between the stellar mass objects we can find in binaries and the supermassive ones we can find in galactic centers. Very few are confirmed anywhere. Their formation mechanisms are debated. And there is no observational constraint of any strength on how many of them might be drifting through void interiors, because there is no method that would detect one if it were there. And the void is a good place to appreciate just how little a black hole needs to do to remain invisible. A supermassive black hole of 100 million solar masses has an event horizon about 2 astronomical units across, which is roughly the size of the orbit of Mars. That is an enormous object by any human standard, and a vanishingly small one at 700 million light-years. It would subtend an angle so small that resolving it would require a telescope larger than the Earth's orbit. The Event Horizon Telescope managed to image the shadow of the black hole at the center of our own galaxy, 27,000 light-years away, by linking radio dishes across an entire planet, and that object is glowing furiously within falling gas. A silent one, 25,000 times farther out, presents no target of any kind. That will change, eventually. The Laser Interferometer Space Antenna, planned for the 2030s, will detect the mergers of supermassive black holes across essentially the entire observable universe, and it will measure recoil velocities directly rather than inferring them from displaced quasars. LIGO and its partners have already catalogued around 100 stellar mass mergers, and the distribution of spins in that catalogue constrains how often the superkick configuration actually occurs. The gravitational wave catalogue is doing something else useful in the meantime. Every merger it records carries information about the spins of the two objects that merged, encoded in the precise shape of the waveform. As the catalogue grows, the distribution of those spins becomes measurable, and the spin distribution is exactly what determines how often nature produces the superkick configuration. So the question of how many black holes have been thrown out of galaxies is being answered indirectly from a completely different kind of observation, by instruments that never look at a void at all. Every object on this list so far, though, shares one property. Every one of them was made inside a galaxy and then lost. The stars, the planets, the remnants, the black holes at every scale, all of them formed where matter was dense enough to make things, and only afterwards ended up where matter is not. The next entry was never inside a galaxy at all. Number 5. The primordial black holes. We are halfway down this list, so it is worth stopping for a moment to look at what has already been added back into a region that is supposed to be empty. We began with 60 galaxies and a discovery from 1981. We added an unknown but probably substantial population of galaxies that are simply below the detection threshold, on the grounds that our own local group would register as 4 or 5 objects if it were placed out there. We weighed the whole volume and found 4 quadrillion solar masses, 2 to 3,000 Milky Ways worth, most of it in dark matter halos that reionization prevented from ever forming a star. And we added tens of billions of unbound stars, planets and remnants drifting between all of it. Everything on that list, though, is a thing that formed inside a galaxy, or would have formed a galaxy if the gas had cooperated. From here down, the list changes character. The remaining entries were not made by galaxies. Some of them were made before galaxies existed, and some of them are not made of matter at all. Which brings us to a hypothesis that has been proposed, rejected, revived, constrained, and refused to die for almost 60 years. Black holes do not have to come from stars. That is the whole idea in one sentence, and it is worth pausing on how unusual a suggestion it is. Every black hole anyone has ever confirmed formed the same way. A massive star ran out of fuel, its core collapsed, and gravity won. That pathway sets a minimum mass, because a star has to be above a certain mass to collapse at all, and it sets a maximum age, because you have to wait for stars to exist and then wait for them to die. But black holes are not a stellar phenomenon in principle. A black hole forms whenever enough mass is packed inside a small enough radius, and it does not care how the packing happened. And in the very early universe, there was a period during which the packing could have happened on its own. Yakov Seldovich and Igor Novikov proposed the mechanism in 1967, and Stephen Hawking developed it in 1971. The reasoning goes like this. The early universe was very nearly uniform, but not perfectly so. The cosmic microwave background records the density fluctuations at the time of recombination, and they are tiny, about 1 part in 100,000. But that is a measurement at one particular scale. On much smaller scales, in the first fraction of a second, The fluctuation amplitude is not directly measured and is not strongly constrained. If any region had a density fluctuation of order unity rather than 1 part in 100,000, meaning it was roughly twice as dense as its surroundings rather than fractionally denser, that region would have collapsed directly into a black hole within the first instance, with no star involved at any stage. The mass of the resulting object is set by how much matter was inside the cosmological horizon at the moment of collapse, which means the formation time picks the mass exactly. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. Collapse at 1 second after the beginning produces something around 100,000 solar masses. Primordial black holes are therefore not one kind of object. They are a whole potential spectrum, running from mountain-sized to supermassive, and which part of the spectrum exists depends entirely on what the fluctuation amplitude was at each scale. Why anyone takes this seriously in 2026 comes down to economy. If dark matter is primordial black holes, then dark matter requires no new particle, no extension to the standard model, and no undiscovered physics whatsoever. It requires only gravity, which we know exists, and an early universe that was slightly lumpier on small scales than the simplest inflationary models assume. Set against 40 years of increasingly sensitive underground detectors finding nothing, that economy is not a small argument. The Hawking radiation part of this deserves a little more attention, because it is one of the few places in physics where black holes behave in a way that is genuinely backwards from intuition. A black hole radiates at a temperature inversely proportional to its mass. Large black holes are cold. Small black holes are hot. A black hole the mass of the Sun has a temperature of about 60 billionths of a Kelvin, which is unmeasurably cold. A black hole the mass of a large asteroid has a temperature in the region of tens of thousands of Kelvin. And a black hole the mass of a mountain, in the surviving window, sits somewhere in between, radiating slowly and steadily and losing mass as it does, which means the process accelerates. As a black hole radiates, it loses mass, and as it loses mass, it gets hotter, and as it gets hotter, it radiates faster. The end of the process is not a fade, but a burst. That is why the constraint at the bottom of the mass range is so firm. The population of primordial black holes light enough to have finished evaporating by now would have produced a specific, calculable, cumulative flash of gamma rays across cosmic history, and the sky does not contain it. For the objects in the surviving window, the picture is the opposite. They are colder than the cosmic microwave background, which means they are currently absorbing more energy than they emit. Like the isolated stellar black holes from the previous entry, they are growing, imperceptibly, and will continue to grow until the universe cools below their own temperature, at which point they will begin the long slide toward evaporation. That slide will take something on the order of 10 to the 34th years, against a current universe age of about 14 billion. The idea had a substantial revival at a specific moment, and it is worth naming it. In February 2016, the LIGO collaboration announced the first direct detection of gravitational waves from a merger observed the previous September and catalogued as GW150914. The two black holes that merged weighed roughly 36 and 29 solar masses. That was heavier than most stellar evolution models had comfortably predicted for black holes formed in the nearby universe, and it was noticed immediately. Within months, several groups, including Simeon Bird and collaborators and Misao Sasaki and collaborators, published arguments that the merger rate LIGO was reporting could be accounted for if some fraction of dark matter consisted of primordial black holes in exactly that mass range. That window has since been closed, and this is where the entry has to be scrupulous, because the constraints on this hypothesis are severe, and stating them properly is the only way the surviving possibility means anything. From the bottom end, Hawking evaporation rules out everything below about 10 to the 15th grams. Black holes radiate, and the smaller they are, the hotter and faster they radiate. So any primordial black hole below that mass would have finished evaporating by now. Its final moments would produce a burst of gamma rays, and the accumulated bursts from the whole population would show up in the diffuse gamma ray background. They do not. From the middle, microlensing surveys have done enormous damage. The Macho, Eros, and Ogle projects monitored millions of stars in the Magellanic Clouds and the galactic bulge for years, looking for the brightening that occurs when a compact object passes in front of one. If dark matter were made of objects between roughly 10 to the -7th solar masses and around 10 solar masses, those surveys would have recorded far more events than they did. That entire band is excluded as the dominant component. A particularly clever survey closed much of what remained at the light end. Hiroko Niyokura and collaborators, reporting in 2019, used Subaru's Hyper-Suprime Cam to image the Andromeda Galaxy repeatedly at a very rapid cadence, taking a full-frame exposure every couple of minutes for a whole night. That cadence is fast enough to catch microlensing events lasting only minutes, which is what an asteroid mass object crossing in front of a star in Andromeda would produce. They found essentially nothing, and much of the asteroid mass window shut. And from the heavy end, primordial black holes above roughly 100 solar masses would have been accreting gas in the early universe, and the energy they released would have altered the ionization history of the plasma before recombination in a way that would be visible in the microwave background. It is not visible, so they are constrained too. What survives all of that is a window of roughly 10 to the 17th to 10 to the 22nd grams. Asteroid masses. In that band, and only in that band, primordial black holes could still constitute the entirety of dark matter without contradicting a single measurement anyone has taken. That window is narrow, it is genuinely open, and it is the honest basis for what follows. So let us suppose it is the answer and work out what that means for the Boötes Void. The void contains roughly 3.4 quadrillion solar masses of dark matter. Take a representative mass in the surviving window, say 10 to the 19th grams, which is about the mass of a small mountain. Divide one by the other, and the number of individual black holes inside the Boötes Void comes out at around 10 to the 30th. A 1, followed by 30 zeros. Now spread that through the volume and ask how far apart they would be. The answer is roughly 1900 astronomical units. An astronomical unit is the distance from the Earth to the Sun. 1900 of them is about 47 times the radius of Neptune's orbit, or a little over 100th of a light year. Put another way, light crosses the typical gap between two of these objects in about 11 days, which produces a picture worth holding carefully. Under this hypothesis, the emptiest region of the universe is threaded, uniformly, everywhere, with black holes spaced at intervals smaller than the distance to the nearest star from here. Not clustered in the galaxies, not concentrated anywhere, just present, throughout, at a spacing that would seem crowded if you could see them. And the size of each one is what makes the picture properly strange. A black hole of 10 to the 19th grams has a Schwarzschild radius of about 1.5 times 10 to the -11 meters. A hydrogen atom is roughly 10 to the -10 meters across. So the event horizon of each of these objects is around 1/10 the width of a single atom. An object with the mass of a mountain range and the diameter of a fraction of an atom, of which there is one every 1900 astronomical units, throughout a region 330 million light-years across. Nothing about that is detectable with any instrument now operating, or with any instrument seriously proposed. It would not interact with anything. It would not accrete meaningfully, because there is nothing to accrete, and its cross-section is subatomic. It would not emit, because a black hole that small is still far colder than the microwave background. It would simply pass through the void indefinitely. The reason this entry ranks where it does, above everything before it, is a matter of distribution. Every earlier entry was made inside a galaxy and then dispersed, which means its abundance in a void is set by how few galaxies the void contains. Primordial black holes were made before galaxies existed at all in the uniform primordial plasma, at a time when the universe was the same everywhere. Their distribution, therefore, traces dark matter rather than light. They do not thin out where the galaxies thin out. They fill the void at the void's full dark matter density, which is to say, at the density of a few thousand Milky Ways spread evenly through it. The obvious question, once the spacing is stated, is whether any of these things have ever passed through anything of ours. And the answer is that the question is only answerable statistically, because the interaction would be so slight. A mountain mass black hole passing through a planet would deposit a negligible amount of energy along its path, since its gravitational reach at that mass is tiny and its physical cross-section is smaller than an atom. It would not carve a tunnel. It would not leave a crater. It would pass through, deflected by an unmeasurable amount, and continue. Various groups have looked for exotic seismic signatures or unexplained energy deposits that such a passage might produce, and nothing has been found, which is consistent both with the objects existing and with them not existing. It is also worth being clear about what the hypothesis actually requires of the early universe, because it is a specific and testable demand rather than a vague appeal. The cosmic microwave background measures the amplitude of density fluctuations on large scales with great precision, and that amplitude is far too small to make black holes. For primordial black holes to exist in any quantity, the fluctuation spectrum must rise steeply towards small scales, reaching an amplitude thousands of times larger at the relevant scale than at the scale the microwave background measures. Some inflationary models produce exactly that feature. Most do not. So the existence of a primordial black hole population is, in effect, a statement about the shape of inflation, and finding one would be a measurement of physics at energies no accelerator will ever reach. There are ways to test this, and they are being pursued. The most direct is a search for gravitational waves from mergers involving objects below one solar mass, which stellar evolution cannot produce under any circumstances, and which would therefore be a definitive signature. LIGO and its partners have searched. They have found none, and that null result is itself a tightening constraint. The Nancy Grace Roman Space Telescope will extend microlensing sensitivity further down the mass scale and narrow the surviving window further. Some models predict that primordial black holes should be clustered rather than uniformly distributed, which would weaken the microlensing constraints and reopen part of the excluded range, and that possibility is actively debated. There is also a suggestion that primordial black holes solved a different problem entirely. The James Webb Space Telescope has found supermassive black holes existing improbably early in cosmic history, at times when the standard picture struggles to explain how they could have grown so large so fast. A population of primordial seeds, already massive at the beginning, would remove that difficulty at a stroke. And if dark matter is not primordial black holes, then the void's 4 quadrillion solar masses is not a population of objects at all. It is a smooth, structureless sea of particles, passing through everything, arranged in halos we cannot resolve, made of something no experiment has ever caught. Whether the Boötes Void contains 10 to the 30th discrete objects or a featureless invisible fluid is not a detail. It is the difference between two entirely different universes, and we cannot yet tell which one we are living in. That is the state of play for dark matter. The next entry on this list is not a hypothesis at all. It is ordinary matter, the kind that people are made of, and we spent 2 decades unable to find most of it. Number 4. The matter that went missing. Everything up to this point has involved matter we cannot see for reasons that are, in the end, ordinary. Galaxies too faint. Halos that never ignited. Objects too small and too dark and too far apart. This entry is different, and it is the strangest thing on this list that is not speculative at all, because it concerns matter we can absolutely see, made of protons and neutrons and electrons, the same species of matter that assembles into planets and oceans and people. And for roughly 2 decades, a third of it was missing. Not theorized about. Not debated. Missing from the ledger, with 2 independent measurements insisting it had to exist. Here is how astronomy came to know exactly how much ordinary matter the universe contains, which is the part that makes the shortfall so uncomfortable. There are 2 completely separate methods, and they agree. The first is Big Bang nucleosynthesis. In the first few minutes after the beginning, the universe was hot enough and dense enough for nuclear fusion to occur everywhere at once, and in that brief window it manufactured the light elements, helium, deuterium, and a trace of lithium. How much of each it made depends very sharply on how many protons and neutrons there were per unit volume, because the reaction rates are density dependent. Deuterium is particularly sensitive. It is fragile, and a denser universe destroys more of it. So measure the primordial deuterium abundance, which can be done by looking at absorption in pristine gas clouds along the lines of sight to distant quasars, and you have measured the density of ordinary matter in the universe. The second method is the cosmic microwave background. Before recombination, the universe was a plasma in which photons and ordinary matter were tightly coupled, and gravity and radiation pressure fought each other, setting up sound waves. Those waves left a pattern of hot and cold spots, frozen into the microwave background when the universe went transparent, and the relative heights of the peaks in that pattern depend directly on how much ordinary matter was participating. The Planck satellite measured that pattern to extraordinary precision. 2 methods, drawing on physics separated by 400,000 years and by completely different phenomena, both return the same figure. Ordinary matter makes up roughly 4.9% of the total energy content of the universe. That number is one of the best measured quantities in cosmology. So astronomers went and counted. Every star in every galaxy, estimated from the light. All the cold gas inside galaxies, measured at 21 centimeters. All the hot gas in galaxy clusters, measured in X-rays, which is a much larger reservoir than the stars. The dust, the remnants, everything. The total came to somewhere between 60 and 70% of what the 2 measurements said had to be there. Between 30 and 40% of the ordinary matter in the local universe was simply not in the inventory. It was called the missing baryon problem, and it stood unresolved for something like 20 years, and it is worth sitting with what that meant. We knew, with high confidence, from 2 independent directions, exactly how many protons the universe contained. And we could not find a third of them. Not the exotic component. Not the dark matter, which nobody expects to find directly. The ordinary component. The same kind of matter as the chair you are sitting on. It is worth being precise about what kind of problem that was, because it was not the same kind of problem as dark matter. Dark matter is a shortfall between the gravity we observe and the matter we can identify, and the resolution requires something new. This was different. This was a shortfall between two things we had already counted: the amount of ordinary matter the early universe demonstrably made, and the amount of ordinary matter we could locate in the late universe. Both quantities were about the same substance. Nobody doubted the protons existed. They had been observed, in absorption, in the early universe, in enormous quantity. Then, over 10 billion years, roughly a third of them stopped being findable, and for 2 decades the field could not say where they had gone. Physicists are generally comfortable with unknowns at the edge of theory. This was an unknown in the middle of the accounting, about the most familiar substance there is, and it sat there through the entire era in which cosmology became a precision science. The matter had not gone anywhere, and we knew that too. The Lyman alpha forest, the dense thicket of hydrogen absorption lines that appears in the spectrum of any sufficiently distant quasar, gives a direct census of the intergalactic gas at earlier epochs. At redshifts around 2 to 3, when the universe was 2 to 3 billion years old, the full complement of baryons is accounted for. All of it is visible, in neutral hydrogen, absorbing light. So the matter was there at the beginning, and it is there now. Somewhere in between, most of it became invisible. The answer, developed through the 1990s and 2000s, and confirmed only recently, is that it became invisible by getting hot. The proposed reservoir is called the warm-hot intergalactic medium. It is gas at temperatures between about 100,000 and 10 million Kelvin, spread through the filaments and sheets of the cosmic web at densities of a few particles per cubic meter. And that particular combination of temperature and density is a genuine blind spot, sitting precisely between two techniques and detectable by neither. Consider why. Cool intergalactic hydrogen is detected by ultraviolet absorption because neutral hydrogen atoms absorb at specific wavelengths and imprint lines on the spectrum of anything behind them. But gas at 1,000,000 Kelvin is not neutral. It is fully ionized. The electrons have been stripped away, and an ionized hydrogen nucleus is a bare proton with no electron transitions and therefore no absorption lines at all. It has become spectroscopically silent in the band where we do most of our looking. Meanwhile, very hot gas is detected by its X-ray emission, which is how the enormous reservoirs in galaxy clusters were found. But X-ray brightness scales with the square of the density, which is brutal. Cluster gas is dense enough to glow. Intergalactic gas at a few particles per cubic meter is thousands of times thinner, and squaring that difference puts its emission far below any X-ray telescope's sensitivity. So the missing baryons were too hot for the ultraviolet method and too thin for the X-ray method. They were hiding in the gap between two instruments, and the gap is exactly where most of the ordinary matter in the universe turned out to be living. Finding it took two very different approaches, and both are worth telling. The first came in 2018 from Fabrizio Nicastro and collaborators, and it worked by absorption rather than emission, which sidesteps the density squared problem entirely. They took a very long exposure with the XMM Newton X-ray Observatory of a bright blazar catalogued as 1E S1553+113, which is essentially a searchlight at cosmological distance. Then they searched its spectrum for absorption lines from highly ionized oxygen. Oxygen is the right element to look for because it is the most abundant heavy element, and because at warm-hot temperatures it is stripped down to a few remaining electrons in a way that produces sharp, identifiable X-ray absorption lines. They found two systems of oxygen-7 absorption, meaning oxygen that has lost 6 of its 8 electrons, at redshifts of roughly 0.43 and 0.36. The column densities matched what simulations of the warm-hot medium had been predicting for years. The paper's conclusion was unusually blunt for the field. The missing baryons have been found. That result is influential, and it is also contested, as X-ray absorption line detections at the edge of an instrument's sensitivity generally are, and it should be presented that way. The second approach is cleaner, and it came from a direction nobody would have predicted 20 years ago. It uses fast radio bursts. A fast radio burst is a flash of radio emission lasting a few milliseconds, arriving from a galaxy hundreds of millions or billions of light-years away, releasing in that instant more energy than the sun produces in days. What makes them useful here has nothing to do with what causes them, which is still debated. It has to do with what happens to the signal on the way. Radio waves traveling through ionized gas are slowed, and the slowing is frequency-dependent. Lower frequencies are delayed more than higher ones. So a burst that leaves its source as a single sharp pulse arrives at Earth, smeared across time, with the high frequencies arriving first and the low frequencies trailing behind by a fraction of a second. The size of that delay is called the dispersion measure, and it is a direct integral of the total number of free electrons along the entire path from the source to us. Every ionized particle in the intergalactic medium contributes. It does not matter how thin the gas is, because dispersion is a line integral rather than an emission process, and it does not matter how hot the gas is, because free electrons disperse a radio signal regardless of temperature. The technique is exactly matched to the problem. What was needed was distance. A dispersion measure on its own tells you the electron column, but not how far the signal traveled. So in 2020, Jean-Pierre Macquart and collaborators used a set of fast radio bursts that had been localized to their host galaxies by the Australian Square Kilometre Array Pathfinder, with the host redshifts measured optically. That gave them both numbers for each burst, how many electrons along the path, and how long the path was. They plotted one against the other, and the relationship that emerged, now called the Macquart relation, is a direct weighing of the ionized baryon content of the intergalactic medium. The answer matched the value from the microwave background and from nucleosynthesis. The missing 30 to 40% of the ordinary matter in the universe is ionized gas, between the galaxies, in exactly the place and in exactly the state the warm-hot medium picture predicted. A third method deserves a mention because it found the gas in a completely different way again. The Sunyaev-Zeldovich effect occurs when a photon of the cosmic microwave background scatters off a fast-moving free electron and picks up a small amount of energy in the process. Hot ionized gas anywhere along the line of sight therefore leaves a faint spectral distortion in the microwave background behind it. The effect from a single intergalactic filament is far too weak to see. But select a large number of pairs of galaxies that are likely to be connected by a filament, stack the microwave background signal in the space between each pair, and the distortion emerges from the noise. It has been done more than once, and it produced a detection of filament gas consistent with everything else. Better instruments are being built for this specific job. The oxygen absorption lines that Nicastro's team hunted sit in the soft X-ray band, and detecting them reliably requires spectrographs with resolution well beyond what XMM Newton and Chandra were designed for. The Athena mission and a proposed instrument called the Line Emission Mapper are both intended to map the warm-hot medium properly, rather than glimpse it in a handful of sightlines. When they fly, the intergalactic gas stops being an inference and becomes a map. The fast radio burst program is expanding as well. Localizations now extend past redshift 1, meaning the Maquart relation can be traced back into the era when the universe was less than half its present age, tracking how the ionized gas budget changed over cosmic time. There are hundreds of localized bursts now, where there were a handful in 2020, and each one is another rod dropped through the intergalactic medium. Now apply all of it to the Boötes Void, because this is where the entry earns its rank. Ordinary matter is roughly 15 to 16% of the total matter budget. 15% of the Void's 4 quadrillion solar masses comes to something on the order of 600 trillion solar masses of ordinary atoms. Several hundred Milky Ways worth of hydrogen and helium inside the region we have been calling empty. And unlike the dark matter, this is matter that could in principle be seen, if it were in the right state. It is not in the right state. Working from the cosmic mean baryon density and the Void's factor of 5 underdensity gives a figure of roughly 1 hydrogen atom per 20 cubic meters of void space. That number needs comparisons to mean anything, so here are 2. Inside the Milky Way, the interstellar medium runs at around 1 million particles per cubic meter, and that is already considered a hard vacuum by any laboratory standard. And the best extreme high vacuum chambers ever constructed on Earth, using cryogenic pumping and hours of baking to drive gas off the chamber walls, reach roughly 10 million particles per cubic meter and are regarded as a triumph of engineering. The average cubic meter of the Boötes Void is emptier than the emptiest volume any human being has ever produced, by something like a factor of 100 million. And now the part that reframes the whole thing. That gas is not cold. Shock heated over billions of years by the gravitational infall that assembled the cosmic web, and further heated by energy injected from supernovae and from active galactic nuclei blowing material out of their host galaxies, the intergalactic medium sits at hundreds of thousands to millions of Kelvin. In void interiors it is cooler than in the dense filaments, but it is still a plasma, and it is still enormously hotter than anything the word void suggests. So the correct description of the contents of the Boötes Void is this: a plasma at a temperature of hundreds of thousands to millions of degrees, at a density of about 1 atom per 20 cubic meters. It is invisible not because it is cold and dark, but because it is hot and thin. Which is the exact opposite of the intuition the word empty produces. And it is worth letting that turn over slowly, because almost every mental image anyone carries of intergalactic space has the sign wrong. Imagine holding a hand out into a cubic meter of it. The gas there is at 1 million degrees. It would not burn. It would not register as warm. It would not register at all, because temperature is a measure of energy per particle, and there is, on average, less than 1 particle in the volume your hand sweeps through. Perhaps a single hydrogen nucleus arrives, moving at 100 kilometers per second, strikes, and is gone, depositing an amount of energy so small that no instrument would record it. The 1 million degrees is real. The heat is not, because heat requires something to be hot. And while your hand is out there, other things are passing through it in enormous numbers. The cosmic microwave background fills all of space uniformly at roughly 410 photons per cubic centimeter, which is 410 million per cubic meter. Those photons are the cooled remnant of the fireball, arriving from every direction at once, at a temperature of 2.725 Kelvin. Alongside them, the cosmic neutrino background, released 1 second after the beginning and never directly detected, contributes around 336 particles per cubic centimeter, and they pass straight through the atoms of your hand without touching anything at all. Set those numbers against 1 hydrogen atom per 20 cubic meters, and the arithmetic produces the sentence this entry has been building toward. In the Boötes Void, there are roughly 8 billion photons of the cosmic microwave background and a comparable number of relic neutrinos for every single atom of ordinary matter. The void is not mostly empty of things. It is overwhelmingly full of the two most abundant particle species in the universe, and almost entirely devoid of the one species we happen to be made of. There is a practical consequence of that density worth stating, because it is the one figure in this entry that a person could act on. A spacecraft crossing the entire Boötes Void at 10% of the speed of light, a journey of roughly 3.3 billion years, would sweep up a total of a few grams of hydrogen along the way. 330 million light-years of travel, and the accumulated interstellar dust and gas would not fill a spoon. Interstellar travel within a galaxy has to contend seriously with erosion from the medium at relativistic speeds. Crossing a void, that problem essentially disappears, which is the only sense in which the emptiness is convenient. The neutrinos are worth one further moment, because they are the most abundant massive particles in the universe, and nobody has ever caught one from that population. Relic neutrinos decoupled from everything else 1 second after the beginning, when the universe was still a plasma, and they have been traveling freely ever since. They are older than the microwave background by roughly 400,000 years, which makes them the oldest thing that reaches us from anywhere. Their energies are now so low that detecting them is at the very edge of conceivable experiment, and at least one project, called Ptolemy, has been designed specifically to try. If it works, it will be a direct measurement of the universe at 1 second old, taken in a laboratory. And they matter for a void in a way they do not matter elsewhere. Neutrinos have a small but non-zero mass, and because they move so fast, they do not fall into structures the way ordinary matter and dark matter do. They stream freely, smoothing out the small-scale structure they pass through. In dense regions, that effect is swamped by everything else. In void interiors, where nothing else is going on, the free-streaming neutrino background is a proportionally larger part of the picture, and the statistics of void sizes and shapes across the sky are one of the ways cosmologists constrain how much neutrinos actually weigh. There is one more thing worth saying about the void's gas specifically, because it sets up the next entry. Void gas is the least processed material in the universe. It has not fallen into a galaxy, been enriched by supernovae, been cycled through a star, or been blown back out by an active nucleus. Its composition is closer to primordial than gas anywhere else, and its motions are gentler, which means that a void preserves things that everywhere else destroys, including something written into it before there were atoms at all. Number 3, the fossil magnetic field. Every galaxy has a magnetic field. That is a sentence most people have never had cause to think about, and it turns out to conceal one of the more stubborn unsolved problems in astrophysics. The Milky Way's magnetic field runs at around 5 microgauss, which is about 100,000 times weaker than Earth's, and it is not a random tangle. It follows the spiral arms. It threads the disk coherently over tens of thousands of light-years. Galaxy clusters carry fields of a few microgauss running through their hot gas. Magnetic fields are everywhere in the universe, at every scale we have measured, doing organized things. The standard explanation for how they got that way is the dynamo. A rotating, turbulent, electrically conducting fluid will stretch and fold any magnetic field lines running through it, and the folding amplifies the field, converting the kinetic energy of the motion into magnetic energy. Galaxies are exactly such a fluid, rotating for billions of years, and the dynamo mechanism accounts well for the strength and structure of the fields we see. But a dynamo is an amplifier. It multiplies an existing field. It cannot start from nothing because there is nothing to stretch and fold. So something had to make the very first magnetic field in the universe, before galaxies existed, and what that something was is genuinely not known. There are candidates. The most conservative is the Biermann battery, named for Ludwig Biermann, the astronomer who also first deduced the existence of the solar wind from the way comet tails behave. The Biermann mechanism generates a weak electric current wherever the pressure gradient and the density gradient in an ionized gas point in different directions, which happens naturally around the edges of the first ionization fronts as they swept outward from the first stars. It produces a real field, but a very weak one, and whether it produces enough to seed everything else is argued about. The more ambitious candidates place the origin far earlier. A magnetic field could have been generated during one of the phase transitions in the very early universe, the electroweak transition at around 10 to the -11 seconds, when the electromagnetic and weak forces separated, or the quark-hadron transition at around 10 to the -5 seconds, when free quarks first became confined into protons and neutrons. Or it could have been generated during inflation itself, in the first unimaginable fraction of a second, and then stretched along with everything else to cosmological scales. The reason this matters here is that a void is the only place where the answer could still be readable. Inside a galaxy, whatever the original field was has been amplified by many orders of magnitude and scrambled by billions of years of turbulence, differential rotation, supernova shocks, and gas flows. Whatever information the seed field carried about its own origin is gone, overwritten many times. It is like trying to read the first draft of a document that has been revised continuously for 13 billion years. Inside a void, there is no dynamo. There is no rotation to speak of, essentially no turbulence, and almost no plasma motion. Any magnetic field present in a void has been stretched and diluted by the expansion of the universe, which is a simple and calculable process, but it has never been reprocessed. If a primordial magnetic field survives anywhere in something resembling its original form, the interior of a region like the Boötes Void is where? Which leads to the obvious question of whether there is any field in there at all, and to one of the more satisfying measurements in modern astronomy, because the answer came from a chain of reasoning that starts nowhere near voids. It starts with blazars. A blazar is a galaxy with an actively feeding supermassive black hole whose relativistic jet happens to point almost directly at us, and some of them emit gamma rays at tera-electron-volt energies, which is roughly 1 trillion times the energy of visible light. Those photons cannot cross the universe untouched. Space is filled with the extragalactic background light, the accumulated glow of every star that has ever shone, and a tera-electron-volt gamma ray, colliding with one of those infrared photons, will convert into an electron and a positron. The pair carries away the energy. Now those particles are moving through space at nearly the speed of light, surrounded by the cosmic microwave background. When a relativistic electron collides with a low-energy photon, it kicks that photon up to much higher energy, a process called inverse Compton scattering. So each electron and positron proceeds to boost microwave background photons into the giga-electron-volt range. The conclusion is unavoidable. Every tera-electron-volt blazar should be accompanied by secondary emission at giga-electron-volt energies, either a faint halo of it spread around the source or a delayed echo arriving after the primary signal, depending on the geometry. This is not a speculative prediction. It follows from well-established particle physics, with no free parameters. The Fermi Gamma Ray Space Telescope looked for that secondary emission. For several sources, including the blazars catalogued as 1ES0229 plus 200, 1ES0347 minus 121, and 1ES1101 minus 232, it was not there. In 2010, Andrei Neranov and Yevgen Vovk published the explanation in Science. The electrons and positrons are charged, and charged particles moving through a magnetic field are deflected. If there is even an extraordinarily weak magnetic field along the path, the pairs are bent away from the original beam direction before they can scatter, and the secondary gamma rays are spread over an angle too wide to detect as a point source. The emission is not absent. It is smeared out below the threshold. Turn that around, and the absence becomes a measurement. The amount of deflection required to hide the signal implies a minimum field strength, and the number Neranov and Vovk arrived at was roughly 3 × 10⁻16 Gauss. And here is the part that belongs specifically to this video, and that is usually left out of summaries. The path from a distant blazar to Earth runs about 80% through voids, because voids are about 80% of the volume of the universe. Nearly all of that deflection happened in void interiors. Neranov and Vovk did not measure the magnetic field of galaxies or filaments. They measured the magnetic field of the empty parts, and they found that it is not zero. The result has held up under scrutiny, which matters, because the whole argument rests on an absence, and absences can have mundane explanations. Joint analyses combining data from the Magic Cherenkov telescopes with Fermi observations of 1 ES0229 + 200, published in 2023, refined the bound using better light curves. The exceptionally bright gamma-ray burst of October 2022, catalogued as GRB 221009A and nicknamed the brightest of all time, was analyzed the same way and produced a compatible constraint. The precise number moves around between roughly 10 to the -17 and 10 to the -16 Gauss, depending on what you assume about the field's coherence length, but the qualitative conclusion has been stable for 15 years. It is worth understanding why the coherence length matters so much, because it is the largest source of uncertainty in the whole measurement, and it says something about what the field is. A magnetic field has a strength, but it also has a scale, over which it points consistently in the same direction before turning. If the field is coherent over enormous distances, then a charged particle traveling through it is deflected steadily in one direction, and a very weak field is enough to do the job. If the field reverses direction every few thousand light-years, then the deflections partly cancel out, like a walk that keeps changing course, and a much stronger field is needed to produce the same net effect. So the same non-detection of gamma rays translates into different field strengths depending on which picture you assume, and the difference can be an order of magnitude or more. That is not merely an inconvenience. The coherence length is itself a clue about origin. A field generated during inflation would be stretched to enormous coherence lengths, potentially larger than any structure in the universe. A field generated at a phase transition would start with a coherence length set by the size of the cosmological horizon at that moment, which was extremely small, and would grow only slowly afterward. So measuring both the strength and the coherence length would discriminate directly between the candidate mechanisms, and simulations of magnetogenesis produce very different predictions for each combination. The measurement that would settle where the first magnetic field came from is a measurement of a void. There is a second reason to care about this field, and it has nothing to do with cosmic origins. Void magnetic fields determine where ultra-high energy cosmic rays come from, or rather, whether that question is answerable at all. The highest energy cosmic rays ever detected carry the kinetic energy of a well-struck tennis ball concentrated into a single subatomic particle, and nobody knows what accelerates them. If we could trace their arrival directions back to their sources, we would know. But cosmic rays are charged, so their paths bend in whatever magnetic fields they cross, and most of their journey is through voids. A void field of 10 to the minus 16 Gauss bends them by an amount small enough that cosmic ray astronomy is possible in principle. A field 1,000 times stronger would scramble their directions completely and close that avenue permanently. The bound from the blazars is therefore also a statement about what kinds of astronomy the universe will permit. Now let us contextualize what 10 to the minus 16 Gauss actually means, because the number is meaningless without a comparison. Earth's magnetic field at the surface is about half a Gauss. That is the field that turns a compass needle and steers the aurora. A refrigerator magnet is around 50 Gauss. A hospital MRI machine runs at tens of thousands of Gauss. The field in the Boötes Void is on the order of 10 to the minus 16 Gauss. That is roughly 1,000 trillion times weaker than the field a compass responds to. To gather as much magnetic energy as is stored in a single household magnet, you would need to collect the field from a volume of void space considerably larger than the solar system. It is, in every practical sense, nothing. And it is measurably, demonstrably, not nothing, which is the entire point. What that faint field might be a record of is the interesting part. A magnetic field frozen into an expanding, electrically conducting medium weakens in a completely predictable way. Its strength falls as the square of the expansion factor, because the field lines are being spread over a larger area. That is simple physics with no free parameters. So run the void's present-day field backward through 14 billion years of expansion, and it corresponds to a substantially stronger field in the early universe. If that field was generated at the electroweak phase transition, then the magnetism now sitting in the Boötes Void is a direct physical relic of the universe at 10 to the minus 11 seconds old. Not an inference about that moment. Not a calculation. The actual field, stretched out but never rewritten, still there, threading a region 330 million light-years across. Nothing else that survives to the present day remembers that instant. The atoms did not exist. The nuclei did not exist. The protons themselves had not yet formed. The magnetic field, if it is primordial, predates all of them. And there is a sharper possibility still, though it is unconfirmed and must be labeled as such. A magnetic field can have helicity, which is a handedness, a preferred sense of twist in the way the field lines wind around one another, like the difference between a left-handed and a right-handed screw. Ordinary processes do not produce a preferred handedness, because they have no reason to prefer one. But a field generated during a process that violated parity in the early universe would carry a net helicity, and parity violation in the early universe is exactly what is required to explain why there is more matter than antimatter, which is to say why anything exists at all. Searches for a preferred handedness in the arrival directions of gamma rays, including work by Hiroyuki Tashiro, Wenlei Chen, Francesc Ferrer, and Tanmay Vachaspati, around 2014, have produced tentative hints of exactly such a signature. Tentative is the correct word. The result has not been confirmed, the statistical significance is modest, and it may not survive better data. It should not be presented as established. But consider the shape of the claim, even as a possibility. The reason the universe contains matter rather than nothing might be recorded, faintly, as a twist in the magnetism of the emptiest place we know how to find. It is a reminder of how indirect the best evidence in astronomy often is. Nobody put an instrument in a void and measured a magnetic field. What happened is that a telescope in orbit did not see gamma rays it had every reason to expect, from objects billions of light-years away, and the only way to make that absence consistent with known particle physics was to conclude that something extremely faint had bent a stream of electrons somewhere along the way. The chain has 4 links in it, and every link is standard physics, and the conclusion at the end of it is a number describing a place no one will ever visit. The Cherenkov telescope array will substantially improve the tera-electron volt measurements this whole line of work depends on, and when it does, the bound on the void field will tighten from both directions, and the helicity question may become answerable. There is one more connection worth drawing, back to the previous entry. The void's ordinary matter is a plasma, and a plasma is electrically conducting, which means the gas and the magnetic field are not independent of each other. Field lines are effectively frozen into an ionized gas. The gas cannot move across them freely, and they cannot move without dragging the gas. In practical terms, this affects how heat travels through the intergalactic medium, because electrons conduct heat far more easily along field lines than across them. A magnetized void conducts heat anisotropically, which sounds like a footnote, and is in fact one of the things that determines the temperature structure of the warm-hot medium that holds most of the ordinary matter in the universe. So the 2 entries are not separate inventories. The million-degree plasma of the previous entry and the fossil field of this one are the same physical system, and each one partly determines the behavior of the other. Which is a reasonable place to notice that a void is not a list of contents sitting in a container. It is a functioning physical environment with its own thermodynamics and its own electrodynamics, running quietly at a density where nothing announces itself. There is a general principle underneath this entry that is worth stating directly because it applies well beyond magnetism. The places where things happen are the places where the record gets erased. Galaxies are where matter has been processed, recycled, blown apart and reassembled, over and over. Everything interesting has happened there, and the cost of everything interesting happening is that the original state is unrecoverable. A void is a place where nothing has happened since the beginning, and that is precisely what makes it an archive. Every entry on this list so far has been a thing the void contains. The next one is a thing the void might have been chosen for. Number 2, the ones who might have chosen the dark. This entry is a hypothesis rather than a measurement, and it is going to be presented as one. There is a real published literature behind it, written by serious people in peer-reviewed journals, and the whole value of including it lies in laying out the argument accurately rather than dressing it up as a discovery. So we will take it in 4 parts: the physics it rests on, the proposals that have been made, the strongest objection to those proposals, and what survives that objection. The physics begins in 1961 in an IBM laboratory with a man named Rolf Landauer asking a question about computers that turned out to be a question about thermodynamics. Landauer wanted to know the minimum energy cost of a computation. The answer he found is subtle, and it has been experimentally confirmed. Most operations a computer performs can, in principle, be made thermodynamically free, because they are reversible. If you know the output and the operation, you can reconstruct the input, and no information has been lost. But some operations destroy information. Erasing a bit is the clearest example. When a bit is erased, 2 possible prior states become one, and there is no way to recover which one it was. Landauer showed that destroying information in that way has an unavoidable thermodynamic price. Erasing 1 bit must dissipate at least Boltzmann's constant multiplied by the temperature multiplied by the natural logarithm of 2 as heat into the surroundings. That is now called the Landauer limit, and it was demonstrated experimentally in 2012 by a group led by Eric Lutz, using a single microscopic particle held in an optical trap, measuring the heat released as its state was reset. Notice the temperature in that formula, because it is the whole of this entry. The minimum cost of computation is directly proportional to the temperature of the environment you are computing in, not to the energy available. To the temperature. The numbers make the point better than the formula does. At room temperature, around 300 Kelvin, the Landauer limit works out to about 2.9 times 10 to the minus 21 joules per bit erased. At the temperature of the cosmic microwave background, 2.725 Kelvin, the same operation costs about 2.6 times 10 to the minus 23 joules. That is roughly 110 times cheaper. The same energy store buys 110 times more thinking, purely by being somewhere colder. And the microwave background is still cooling, which means that figure keeps improving, forever. There is a further piece of the theory that sharpens the argument considerably, and it came from Charles Bennett, also at IBM, working through the 1970s. Bennett showed that computation itself can in principle be made entirely reversible, and therefore entirely free. If you never discard information, you never pay the Landauer cost. You can arrange a computation so that every step can be run backwards, and the energy borrowed to perform it can be recovered at the end. The catch is that reversible computation requires you to keep everything. Every intermediate result, every discarded branch, every scrap of working. The memory requirement grows without bound, and eventually you have to erase something in order to keep going. So the practical structure of the argument becomes this. The only unavoidable thermodynamic cost of thinking is the cost of forgetting, and that cost is set by the temperature. A civilization can defer the bill by remembering more. It cannot avoid it forever. And when the bill comes due, it is cheaper if the universe is colder. Put those pieces together, and a picture emerges that is quite different from the usual image of an advanced civilization. The usual image is enormous energy consumption, structures around stars, harvested galaxies, power on scales that dwarf anything human. But energy is not scarce. A single ordinary star radiates more energy in 1 second than human civilization has used in its entire history, and there are hundreds of billions of them in one galaxy. What is scarce is somewhere to put the heat afterwards, and that scarcity is governed by temperature alone. The first person to take that seriously as a long-term proposition was Freeman Dyson in 1979, in a paper published in Reviews of Modern Physics titled Time Without End, Physics and Biology in an Open Universe. Dyson asked whether life could persist indefinitely in a universe that expands and cools forever, given that any finite civilization has a finite supply of usable energy. His conclusion was that it could, but only by changing its relationship with time. A civilization that scaled its own metabolism down in step with the falling temperature of the universe, spending long stretches dormant and waking only in brief bursts of activity, could perform an infinite number of computations on a finite energy budget, because each successive computation would cost less than the one before. The strategy is not to hoard energy. The strategy is to wait for the price to drop, and the price drops on its own, forever. That paper is the foundation of a small field now called physical eschatology, and it is not a fringe document. It is one of the most cited papers on the long-term future of the universe. The application to voids came later. In 2006, Milan Cherkovich and Robert Bradbury published a paper in New Astronomy titled Galactic Gradients, Post-Biological Evolution and the Apparent Failure of SETI. Their argument, compressed, runs as follows. Any civilization that persists long enough is likely to become post-biological, meaning that its activity is dominated by information processing rather than by anything that requires a planet, a star, or a biosphere. For such a civilization, the binding constraint is not the supply of energy, which is abundant, but the ability to dispose of waste heat, which is limited by the temperature of the surroundings. Therefore, an advanced civilization would not migrate inward toward the energy-rich, star-dense, warm galactic center, which is where intuition and most science fiction place them. It would migrate outward toward the cool, quiet, sparse periphery. And their conclusion about the search for extraterrestrial intelligence follows directly. SETI has spent 6 decades pointing at sun-like stars in the galactic neighborhood because that is where biology like ours would arise. The argument says that is precisely where a mature civilization would no longer be. A related proposal arrived in 2017 from Anders Sandberg, Stuart Armstrong, and Milan Cherkovich, and it took Dyson's weighting strategy to its conclusion. If computation gets cheaper as the universe cools, and if a civilization has goals that are indifferent to when they are achieved, then the rational policy is to do almost nothing now and act later, because the same energy will accomplish vastly more in the deep future. Under that framing, an apparently quiet universe is not evidence of absence. It is evidence of patience. The proposal has been argued with, which is a sign that it is being treated as a real object rather than a curiosity. Charles Bennett, Robin Hanson, and Jess Riedel published a response in 2019 pointing out that useful energy is itself dissipating over time, so waiting is not free, and the optimal strategy is more complicated than simply sleeping. That exchange is a healthier sign for the idea than agreement would have been. Now apply all of it to the Boötes Void, because on every criterion the argument names, the void scores extraordinarily well. It is dark. There is essentially no starlight, so nothing is being warmed by anything. It is quiet. There are no nearby supernovae, no gamma-ray bursts, no galactic mergers, no passing stars to perturb an orbit or irradiate a structure. It is thermally clean. With almost no gas, there is nothing to conduct heat back into whatever you build, and a radiator can dump entropy in every direction without anything reflecting it back. And it is stable. Over the next 100 billion years, the interior of the Boötes Void will change less than any other region of comparable size, because there is nothing in it capable of changing anything. Every single property that makes the void hostile to biology makes it, on this argument, close to ideal for computation. There is a scale of stability here that is difficult to appreciate without a comparison. Over the next 100 billion years, the Milky Way will merge with Andromeda, pass through the resulting starburst, exhaust most of its remaining gas, and gradually redden as its stars die and are not replaced. It will be a substantially different object. The interior of the Boötes Void, over the same span, will do almost nothing at all. Its 60 galaxies will drift further apart. Its gas will thin further. Nothing will collide, nothing will explode nearby, nothing will pass close enough to disturb anything. If you wanted to place an object somewhere and be reasonably confident of what its surroundings would look like in 100 billion years, there is no better address in the observable universe. And now the objection, which deserves to be stated at full strength rather than waved at, because it is a good one and it is very likely fatal to the simple version of the claim. A void is a terrible place to build anything. The previous entries established the numbers. Roughly 1 hydrogen atom per 20 cubic meters. And that matter is hydrogen and helium, essentially unenriched, because void gas has not been cycled through generations of stars. There is no carbon. There is no silicon. There are no metals. To collect a single gram of raw material, you would have to sweep a volume comparable to a solar system, and what you would collect could not be made into a structure. So a civilization could not build in the void. It could only build somewhere else and then move the finished object, and the nearest somewhere else is 165 million light-years from the center. Moving any substantial mass across that distance requires an energy expenditure so enormous that the thermodynamic savings, real as they are, would take an implausible span of time to repay. The economics do not work, which does not defeat the underlying logic. It relocates it, and the relocated version is more interesting than the original. If waste heat is genuinely the binding constraint on a long-lived civilization, then what such a civilization actually needs is not to live in a void. What it needs is an unobstructed line of sight into one. A void is the best heat sink the universe offers, a direction with no starlight coming back, no radiation pressure, nothing to reflect your entropy into your face, open for the rest of cosmic history. You could build your structures in a galaxy, where the raw materials are, and point your radiators outward into the emptiness. That is a far cheaper strategy than emigration, and it delivers the same thermodynamic benefit. On that reading, the value of the Boötes Void is not as real estate. It is as a direction to face. There is a hard floor on how far the strategy can go, and it is worth naming because it applies to every version of this argument. No passive radiator anywhere in the universe can cool below the temperature of the cosmic microwave background, because the background is arriving from all directions at once and warming everything it touches. That floor currently sits at 2.725 Kelvin. You cannot radiate into a bath that is warmer than you are. So the coldest a structure can passively get, anywhere, in a galaxy or a void or the space between them, is that same 2.725 Kelvin. But the floor is falling. The microwave background cools as the universe expands, and it will keep cooling indefinitely. In 100 billion years, it will be a small fraction of a Kelvin. In 1 trillion years, it will be lower still. Which is exactly the mechanism Dyson identified. The strategy is not to find a cold place, because every place has the same floor. The strategy is to wait, because the floor drops on its own. What a void offers, then, is not a lower floor. It is the ability to actually reach the floor. In a galaxy, a structure is warmed by starlight, by dust, by the diffuse infrared glow of everything around it, and it sits well above the background temperature, no matter how carefully it is engineered. In a void, there is nothing between a radiator and the background but the background itself. Which raises the question of whether anyone has looked, and the answer is that the closest thing to a search was aimed somewhere else. The most serious effort of its kind is the survey led by Jason Wright, called Glimpsing Heat from Alien Technologies, which in 2015 examined data from the Wide-Field Infrared Survey Explorer for around 100,000 galaxies. The logic is straightforward. Any civilization using a substantial fraction of its galaxy's starlight would have to re-radiate that energy as waste heat, which would appear as an excess of mid-infrared emission relative to the visible light. The survey found no unambiguous candidates, though it flagged a small number of galaxies with unusual mid-infrared properties as worth following up. But note what that search was tuned for. It looked for warm structures around stars, radiating at temperatures of hundreds of Kelvin, peaking in the mid-infrared. A cold structure sitting in a void, radiating at 10 Kelvin or 3 Kelvin, would peak in the far infrared and sub-millimeter at wavelengths of hundreds of microns. That is precisely the band where the cosmic microwave background itself and the thermal glow of galactic dust dominate the entire sky. No survey has ever been designed to find such a thing, and it is not obvious how one would be. The wavelength arithmetic is worth spelling out because it explains the problem better than any general statement. A structure at 300 Kelvin, roughly room temperature, radiates most strongly at a wavelength of about 10 microns, in the mid-infrared, which is exactly the band WISE was built to survey, and exactly why the search was feasible. A structure at 10 Kelvin radiates most strongly near 300 microns. A structure at 3 Kelvin peaks near a millimeter. And at those wavelengths, every square degree of sky is already glowing with the cosmic microwave background and with cold dust in our own galaxy. You would be looking for a faint, cold object against a bright, cold background that fills the entire sky at a distance of 700 million light-years. There is one other detection route in principle, and it fails for a different reason. Any sufficiently massive structure bends light, so a large enough object in a void would produce a gravitational lensing signature. But the mass required to produce a measurable lensing effect at that distance is on the scale of a galaxy cluster, and it would additionally need a suitable background source in near-perfect alignment. Both conditions together make the approach hopeless in practice, whatever its merits on paper. Chirkovich and Bradbury's argument carries one further prediction that is worth mentioning, because it inverts a familiar idea. Astronomers talk about a galactic habitable zone, a band within a galaxy where conditions favor the emergence of life, far enough from the crowded, radiation-drenched center and close enough in that heavy elements are abundant. Their argument implies a second gradient running in the opposite direction, in which the desirability of a location for a mature technological civilization increases as you move outward, precisely where the biological habitability is decreasing. If both gradients are real, then the places where intelligence is most likely to begin, and the places where it is most likely to end up, are systematically different regions, and any search built around the first will systematically miss the second. So the honest closing position for this entry is this, and it should be stated plainly rather than left hanging. None of the foregoing is evidence that anything is inside the Boötes Void. There is no observation, no anomaly, and no signal. What there is a chain of thermodynamic reasoning, published in physics journals by people arguing carefully, which points at void interiors as the place where our detection methods are weakest and where our search strategies have never been aimed. That is a statement about the shape of our ignorance. It is not a claim about the void's contents, and the difference between those two things matters. It is also worth being clear that the argument, taken seriously, is not primarily about aliens at all. It is about thermodynamics, and it makes a claim that holds regardless of whether anyone is out there, that the long-term value of a region of space for any process that involves organizing information is set by how cold and how quiet it is, rather than by how much matter it contains. By that measure, the ranking of locations in the universe is close to inverted from the intuitive one. The crowded places are the poor ones. The empty ones are the wealthy ones, in a currency that only becomes spendable later. The Fermi paradox literature has quietly absorbed this point, and it is worth noticing the shift. Voids are increasingly described in that literature not as empty volume, but as unsearched volume. Those are different words, and they carry different obligations. Whatever may or may not have chosen the void, though, one thing did not have to choose it. One thing is simply there, throughout, at full strength, in every cubic centimeter. It is the reason the void exists at all, and it is the reason the void is still growing. Number 1, the only thing that fills all of it. We come to the top of the list, and to the answer this whole countdown has been ranked toward. The thing that fills the Boötes Void completely, throughout its entire volume, at full universal density, with no reduction whatsoever for the void's underdensity, is dark energy. Its discovery has a date. In 1998, 2 independent teams published results from the same kind of measurement. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, whose work involved Brian Schmidt and Adam Rees, had both been using Type 1a supernovae as distance markers. A Type 1a supernova occurs when a white dwarf in a binary system accumulates enough material to trigger runaway carbon fusion, and because the trigger point is set by the same physics every time, these explosions have a characteristic peak brightness. Compare how bright one appears to how bright it should be, and you have its distance. Measure its redshift as well, and you have a point on the graph of how the universe has expanded. Both teams expected to measure how much the expansion had been slowing down, since gravity ought to be pulling everything back together. What they found instead was that the most distant supernovae were fainter than a decelerating universe could account for. They were further away than they should have been. The expansion of the universe has not been slowing. For roughly the last 5 billion years, it has been speeding up. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for that result in 2011. It is worth noting how carefully that result had to be checked, because it overturned an assumption nobody had thought was in question. Type 1a supernovae are not perfectly identical. They vary in peak brightness by a noticeable amount. What makes them usable is a relationship discovered by Mark Phillips, which connects a supernova's peak brightness to how quickly it fades afterward. Brighter ones decline more slowly, and the correlation is tight enough that measuring the light curve lets you correct the peak brightness back to a standard value. Without that correction, the whole method fails. Both teams applied it independently, both worried at length about whether dust or evolution in the supernova population could mimic the signal, and both arrived at the same answer anyway. Something is driving the acceleration, and dark energy is the name for whatever it is. Its identity is unknown, but its behavior is measured, and one property of that behavior decides this entire list. Matter dilutes. That sounds obvious, and it is worth stating precisely because everything else on this countdown obeys it. Double the linear size of a region, and its volume increases eightfold, and the density of everything in it falls by the same factor. Galaxies, gas, dust, dark matter halos, primordial black holes, wandering stars, all of them get thinner as space grows, in exact proportion. Dark energy does not. As far as every measurement has been able to determine, its density is constant in space and constant in time. Expand a region and you do not dilute the dark energy in it. You get more dark energy because there is more space, and each cubic meter of new space arrives carrying the same amount as every other. A cubic meter of space contains roughly 6 times 10 to the minus 10 joules of dark energy, and it contains exactly that amount inside a galaxy, inside a cluster, and in the deepest interior of the Boötes Void. Which is why it stands at the top of a list ranked by how much of the void each candidate fills. Every previous entry was thinned by the void's factor of 5 under density, or was rare to begin with, or was speculative. This one is present at 100% of its universal density in 100% of the volume. On this list's own measure, nothing else is close. Now the scale, and it needs contextualizing twice, because the number is strange in both directions. 6 times 10 to the minus 10 joules per cubic meter is a very small amount of energy. It is roughly what it takes to lift a single grain of table salt 1 millimeter against gravity. That is the entire energetic content of a cubic meter of empty space. It is such a small quantity that it took until 1998 to notice it existed, despite it being everywhere. But multiply it by the volume of a sphere 330 million light-years across, and the total comes to something on the order of 10 to the 64th joules. Convert that to a mass equivalent through Einstein's relation between energy and mass, and the dark energy inside the Boötes Void amounts to roughly 47 quadrillion solar masses. which brings us back to a number from earlier on this list. When we weighed the void's matter, the answer was about 4 quadrillion solar masses, which we said was 2 to 3,000 Milky Ways worth. That number was meant to overturn the idea that the void is empty, and it does. The dark energy filling the same volume outweighs all of it by more than 10 to 1. The most famous emptiness in astronomy is dominated, overwhelmingly, by the one component that emptiness cannot dilute. And it is worth pausing on the logic of that, because it inverts the usual relationship. Everywhere else in the universe, dark energy is a small contributor to the local situation. Inside a galaxy, the local matter density is enormously higher, and gravity wins comfortably. Voids are the only places where dark energy is not just present, but dominant, and it is dominant there precisely because there is so little of anything else. Emptiness does not weaken dark energy. Emptiness is what lets it take over. It is worth admitting how little we understand about the thing we have just placed at the top of this list. Dark energy is measured, and it is not explained. The most natural candidate is the energy of the vacuum itself, which quantum field theory says should not be zero, since even empty space is full of fields fluctuating around their lowest states. That is a satisfying story until you calculate how much vacuum energy the theory actually predicts. The answer comes out larger than the observed value by a factor of around 10 to the 120th power. That is not a small disagreement. It is a 1 followed by 120 zeros, and it is routinely described as the worst quantitative prediction in the history of physics. Something is cancelling almost all of the vacuum energy to 120 decimal places and leaving behind a residue just large enough to determine the fate of the universe. Nobody knows what is doing the cancelling or why it stops where it does. There is also a live question about whether dark energy is constant after all. If its density changes over time, even slightly, the deep future picture that follows in a moment changes with it. Current measurements are consistent with a strict cosmological constant, but they do not require one, and large surveys mapping the expansion history have produced results that some read as hints of evolution. That question is being actively worked on right now, with instruments in operation, and it will probably be settled within a couple of decades. Everything after this point in the entry should be understood as the consequence of the simplest assumption, which is the one currently favored and not the one currently proven. Which means the void is not sitting still. Because it is underdense relative to its surroundings, the gravitational pull holding its contents together is weaker than average, and the surrounding walls and filaments pull outward on everything at its edges. Relative to the universal background, a void behaves as though it repels. Voids expand faster than the mean cosmic expansion rate, and they have been doing so for most of the age of the universe. So the Boötes Void is not a static hole with fixed dimensions. It is growing. It has been growing since the density fluctuation that made it first began to lose the competition with its neighbors, and it is growing now. And the emptiness we have spent this list cataloging is not a condition, but a process that is still running. And that process is measurable, which is not obvious, and is one of the more elegant results in observational cosmology. Consider a photon of the cosmic microwave background crossing a void. On the way in, it falls into the void's shallow gravitational profile and gains a small amount of energy. On the way out, it climbs back out and loses it again. In a universe with no dark energy, the two effects cancel exactly, and the photon emerges unchanged. But in an accelerating universe, the void's gravitational profile flattens while the photon is still inside it, because the void is expanding faster than the surroundings. So the climb out is slightly easier than the fall in was, and the photon emerges with slightly less energy than it arrived with. It comes out a fraction cooler. This is the integrated Sachs-Wolf effect, and by cross-correlating maps of the microwave background with maps of galaxy distribution, it has been detected. Voids leave faint, cool imprints on the oldest light in the universe. The signal from any one void is far too weak to see, so it required stacking thousands of them, but it is there. Which means we have watched dark energy operating on regions like the Boötes Void, using photons that left their source before there were atoms. There is a further reason astronomers care about voids specifically, and it is arguably the most important one. Dark energy might not be a substance at all. A large family of serious alternatives propose instead that gravity itself behaves differently on the largest scales than general relativity predicts, and that the apparent acceleration is a symptom of modified gravity rather than of some new energy filling space. These models go by names like F of R gravity and chameleon and symmetron theories. Every one of them faces the same difficulty. Gravity has been tested to exquisite precision within the solar system, and general relativity passes every test. So any modification has to be hidden in dense environments, and all these models include what is called a screening mechanism to do exactly that, a way for the modification to switch itself off wherever the matter density is high. And screening switches off where density is low, which places the entire question in the hands of voids. If gravity is modified, the deviation from general relativity is largest, cleanest, and least screened inside void interiors. The shape of a void's density profile, the weak lensing signal from stacked voids, the pattern of galaxy motions around void edges, these are among the sharpest tests available for whether dark energy is a substance or a symptom. The Boötes Void is not a curiosity in that program. It is an instrument, and it is being used as one, which is worth appreciating as a reversal in the way this region has been treated. For 4.5 decades, the Boötes Void has been described in popular accounts as a mystery, a hole, an anomaly, a place where the universe went wrong. In the actual working literature, it is nothing of the sort. It is a well-understood consequence of gravity operating on initial conditions we have measured, and it is a piece of laboratory equipment. The emptiness that made it famous is exactly the property that makes it useful, because the only way to test the most important open question in cosmology is to find somewhere with nothing in it. Now the turn, and it is the reason this entry is at the top, rather than merely the answer to a ranking question. Under a cosmological constant, the acceleration does not stop. It continues indefinitely, and it compounds. Everything gravitationally bound stays bound. The local group, our own gravitationally committed neighborhood containing the Milky Way, Andromeda, Triangulum, and their several dozen satellites, is bound and will remain so. The Milky Way and Andromeda will merge in roughly 4 to 5 billion years into a single elliptical galaxy. Not one star will strike another. The systems are far too diffuse for that. But the two will become one. Everything not bound to us, however, is receding, and receding faster with time. And there is a horizon. Under accelerating expansion, the cosmological event horizon sits at roughly 16 billion light-years and is approximately fixed, which means galaxies cross it and do not come back. Once a galaxy is beyond it, no signal from that galaxy will ever reach us again, and no signal from us will ever reach it. It has not gone anywhere. It is simply, permanently, out of causal contact. Abraham Loeb worked through the reachability side of this in 2002. Which galaxies we could still reach if we left today at any speed short of light, and the answer is a surprisingly small fraction. Lawrence Krauss and Robert Scherer laid out the observational consequences in 2007 in a paper with a title that says the whole thing, the return of a static universe and the end of cosmology. Somewhere in the region of 100 to 150 billion years from now, every galaxy outside the local group will have crossed that horizon. And their conclusion is the payoff of this entire video. An astronomer alive at that time, doing careful and honest science with excellent instruments, would look out and see a single galaxy surrounded by nothing at all. The cosmic microwave background would have been redshifted so far that no conceivable detector could register it. The oldest light in the universe would simply be gone. There would be no other galaxies to measure a redshift against, and therefore no evidence that the universe expands. No expansion means no way to run the expansion backwards, which means no evidence of a beginning. No microwave background means no record of the early universe. Every observational pillar that cosmology stands on would have been removed, and nothing would remain to indicate that they had ever existed. That astronomer would conclude, reasonably, with good data and sound methods, that they lived in a single static island of stars in an infinite and eternal void. And they would be wrong, and there would be no way whatsoever for them to find out. It is worth being clear that this is not a catastrophe in any conventional sense. Nothing is destroyed. No star goes out because of it. The galaxies that cross the horizon carry on existing, forming stars, running down at their own pace, entirely unaffected by having become invisible to us. Nothing happens to them at all. What is lost is not matter, but access, and the loss is one-sided only in the sense that it is mutual. They lose us in exactly the same way and at exactly the same moment. And the Boötes Void itself will still be there through all of it, considerably larger. Its walls will have retreated. Its 60 galaxies, which are not bound to each other in any strong sense, will have drifted so far apart that each one will sit alone in a sky containing nothing else, its neighbors long past its own horizon. Whatever void galaxies exist then will each be a universe unto themselves, in the fullest possible sense, and there will be no astronomer anywhere with any means of establishing otherwise. Now listen to Greg Aldering's sentence again, the one from the very beginning of this list. If the Milky Way had been at the center of the Boötes Void, we would not have known there were other galaxies until the 1960s. We treated that as a striking hypothetical about an unlucky address. It is not a hypothetical. It is a forecast. What the deep future calculation says is that the situation Aldering described is not a rare misfortune that befalls observers in one strange region. It is the ordinary and permanent condition toward which every observer in the universe is traveling. The Boötes Void is not an anomaly in the cosmos. It is a preview of the cosmos, arriving early in one place. There is a strange comfort available in that, if you want it. We are not living at an unremarkable moment. We are living at the only kind of moment during which the universe is legible, and we happen to have developed instruments in time to read it. That is not a large window by cosmic standards, and there was no requirement that anyone be here to look through it. And now the last corrections to the number we started with. 60 galaxies where 2,000 were expected. A 97% shortfall. That is where this list began, and it sounded like a description of something missing. Nothing was ever missing. The matter is there, 4 quadrillion solar masses of it, thousands of galaxies worth, sitting in dark halos that reionization prevented from ever lighting. The unbound stars and planets are there, tens of billions of them, one per cube the width of the Milky Way. The ordinary matter is there, hundreds of galaxies worth, at 1,000,000 degrees and 1 atom per 20 cubic meters, too hot to absorb and too thin to shine. The magnetism is there, 10 to the minus 16 Gauss, older than atoms, possibly older than protons. And the dark energy is there at full strength, outweighing all of it by more than 10 to 1, growing in total quantity every second because the region itself is growing. The Boötes Void does not have a deficit of contents. It has a surplus of space to distribute them through. That is the whole answer, and it took the entire list to earn it. And the surplus is still expanding. Every second, the volume gets larger, and the matter inside it gets thinner, and the dark energy total gets bigger, and the walls retreat a little further from the center. What is happening in the Boötes Void is not a strange local condition. It is what is happening everywhere, and it is simply further along there. Consider what the end of that process looks like, from the inside. A world orbiting a star in the merged Milky Way and Andromeda, some 130 billion years from now. The last external galaxy is leaving. Not exploding, not visibly rushing away. Just redshifting, its light stretching slowly toward wavelengths that no instrument can register, dimming smoothly toward zero across millions of years. Nobody watching would see a moment. There would be a night when the deepest available exposure still recorded it, and a night when it did not, and no astronomer alive could say which night the change occurred. There is no event. There is only a sky that used to have something in it, and then a sky that does not. Afterwards, the heavens contain one galaxy and a complete, permanent dark, and everything the universe once was becomes unknowable to everyone who comes after. Which means the window we are looking through is open now and will not stay open. Cosmology exists as a science because we happen to be alive during the narrow interval in which other galaxies are still visible and their motion is still measurable. That interval opened when structure formed, and it will close in 100 billion years or so. Everything anyone has ever learned about where the universe came from, how large it is, and what it is made of, was learned inside it. We did not earn that. We arrived at the right time. So the Boötes Void turns out not to be a hole in the universe at all. It is a room the universe is slowly moving into, and we have simply been given an early look at what that room contains, which is nearly everything, spread nearly infinitely thin, still lit for a little while longer by the galaxies that have not yet gone. Let that hold you for a while. There is no hurry about any of it, and no part of it requires anything from you tonight. Sleep well, and good night.